high level of dopamine baseline are what drove the evolution of our species, and they're really what drive the evolution of anyone's.
I'm going to be doing the section of the free code camp on data analysis. I already watched the introduction, and I'm going to start today. It's just a bunch of series of videos, I think. It's probably close to 4 hours of videos. But first, I'm going to watch this. I already watched this podcast, but I'm watching it again. Really recommend it.
Life progression too. So they're a good thing. Dopamine is a good thing. Just very briefly, because it was also covered in the interview episode I did with Anna Lemke about addiction. Some of you might be asking, what should I do if I experience a drop in my baseline level of dopamine because of engagement with some activity or some substance that led to big peaks? Just to put some color and example on this, a few episodes ago I talked about a friend who I've known a long time. This is actually the child of a friend who has basically become addicted to video games. He decided, actually after seeing that episode with Anna, to do a 30-day complete fast from phone, from video games, and from social media of all kinds. He's now at day 29. He's really accomplished this. Not incidentally, his levels of concentration, his overall mood are up. He's doing far, far better. What he did is hard. In particular, the first 14 days is really hard. But the way that you replenish the releasable pool of dopamine is to not engage in these dopaminergic seeking behaviors. Because remember, typically people arrive at a place where they want to stop engaging in these behaviors or ingesting substances when that dopamine is depleted, when they're not getting the same lift. In his case, he was feeling depressed. He thought he had ADHD. They were starting to treat it as ADHD. And certainly there are people out there who have ADHD, but what he found was that his levels of concentration are back. He does not need to be treated for ADHD. And actually the psychiatrist wondered if he did prior to this video game social media fast. He's feeling good. He's exercising again. I'm not making this up. This is really a very specific but very relevant example of how the dopamine system can replenish itself. Of course, if there's a clinical need for ADHD treatment, by all means pursue that. But I think a lot of ADHD does go misdiagnosed because of this depletion in dopamine that occurs because of overindulgence in other activities and the drop in baseline. So for anyone that's experienced a real drop in baseline who has addictive tendencies, whether or not they're behaviors or substances, that is always going to be the path forward, is going to be either cold turkey or through some sort of tapering to limit interactions with what would otherwise be the dopamine evoking behavior or substance. So let's talk about the
doing this experiment after listening to this podcast of randomizing my days that I increase the activities that give me more dopamine. Just see if it has an influence on my motivation. And so far I've been randomizing with 50-50. And by the end of this week and start of the next week, I'm gonna change to 40-60. And then I think I'm gonna probably maintain that for a while and see how it goes. But so far, I think it has really shown to me that I was too conditioned to wait for a reward after doing something hard. And it's definitely something that changes your level of focus and your life overall, I think. It's really clear when you stop doing things that give you dopamine, like eating sugar or watching a bunch of random videos, stuff like that. I could, after a couple of days of doing nothing, complete dopamine detox, I could really feel it felt painful in my head, actually. And how much that is part of everyone's life, I think. And we don't realize it because our brains are not prepared to live with the internet and all the stimulus we get bombarded each day, everywhere we go.
Optimal way to engage in activities or to consume things that evoke dopamine. And by no means am I encouraging people to take drugs of abuse. I would not do that. I am not doing that. But some of the things on these lists of dopamine evoking activities are things like chocolate, coffee, even if it's indirect, sex and reproduction, provided it's healthy, consensual, context appropriate, age appropriate, species appropriate, of course, is central to our evolution and progression as a species. So certain things like cocaine, amphetamine, I will put in the classification of bad. I'm willing to do that. And other things are part of life, food, exercise, if that evokes your dopamine. How are we supposed to engage with these dopamine evoking activities in ways that are healthy and beneficial for us? How do we achieve these peaks, which are so central to our well-being and experience of life, without dropping our baseline? And the key lies in intermittent release of dopamine. The real key is to not expect or chase high levels of dopamine release every time we engage in these activities. Intermittent reward schedules are the central schedule by which casinos keep you gambling, the central schedule by which elusive partners or potential partners keep you texting and pursuing on either side of the relationship. Intermittent schedules are the way that the internet and social media and all highly engaging activities keep you motivated and pursuing. And we can take this back to our evolutionary adaptive scenario where you are out there looking for water, looking for food. Not every trail, not every pursuit, not every hunch about where the animals will be, where the food will be, where the berries will be. Not every single one of those played out. There's something called dopamine reward prediction error. When we expect something to happen, we are highly motivated to pursue it. If it happens, great. We get the reward. The reward comes in various chemical forms, including dopamine. And we are more likely to engage in that behavior again. This is the basis of casino gambling. This is how they keep you going back again and again and again, even though on average, the house really does win. You can transplant that example to any number of different pleasureful activities. If you're not a gambler and that doesn't appeal to you, I have to imagine there's something that appeals to you, something that you do repeatedly because you enjoy it. And almost inevitably, it's because there's an intermittent schedule. There's an intermittent schedule by which dopamine sometimes arrives, sometimes a little bit, sometimes a lot, sometimes a medium amount. Okay? That intermittent reinforcement schedule is actually the best schedule to export to other activities. How do you do that? Well, first of all, if you are engaged in activities, school, sport, relationship, etc., where you experience a win, you should be very careful about allowing yourself to experience huge peaks in dopamine unless you're willing to suffer the crash that follows and waiting a period of time for it to come back up. What would this look like in the practical sense? Well, let's say you are somebody who really does enjoy exercise. Or let's say you're somebody who kind of likes exercise but forces yourself to do it, but you make it pleasureful by giving yourself your favorite cup of coffee first, or maybe taking a pre-workout drink, or taking an energy drink, or listening to your favorite music, and then you're in the gym and you're listening to your music. That all sounds great, right? Well, it is great, except that by layering together all these things to try and achieve that dopamine release, and by getting a big peak in dopamine, you're actually increasing the number of conditions required to achieve pleasure from that activity again. And so there is a form of this where sometimes you do all the things that you love to get the optimal workout. You listen to your favorite music, you go at your favorite time of day, you have your pre-workout drink if that's your thing. You do all the things that give you that best experience of the workout for you. But there's also a version of this where sometimes you don't do the dopamine enhancing activities. You don't ingest anything to increase your dopamine. You just do the exercise. You don't do the exercise and expect dopamine to arrive through some what we call exogenous source as well. You might think, well, that sounds lame. I want to continue to enjoy exercising. That's exactly the point. If you want to maintain motivation for school, exercise, relationships, or pursuits of any duration and kind, the key thing is to make sure that the peak in dopamine, if it's very high, doesn't occur too often. And if something does occur very often, that you vary how much dopamine you experience with each engagement in that activity. Now, some activities naturally have this intermittent property woven into them, right? We sometimes have classes that we like and other classes we don't like. We don't always get straight A's. Sometimes we don't get rewarded with the outcome that we would like. We don't always have the perfect relationship outcome. But understand that your ability to experience motivation and pleasure for what comes next is dictated by how much motivation and pleasure and dopamine you experienced prior. The reason I can't give a very specific protocol like delete dopamine or lower dopamine every third time is that wouldn't be intermittent. The whole basis of intermittent reinforcement is that you don't really have a specific schedule of when dopamine is going to be high and when dopamine is going to be low and when dopamine is going to be medium. That's a predictable schedule, not a random intermittent schedule. So do like the casinos do, certainly works for them. And for activities that you would like to continue to engage in over time, whatever those happen to be, start paying attention to the amount of dopamine and excitement and pleasure that you achieve with those and start modulating that somewhat at random. That might be removing some of the dopamine releasing chemicals that you might take prior. Maybe you remove them every time, but then every once in a while you introduce them. Maybe it involves sometimes doing things socially that you enjoy doing socially, sometimes doing the same thing but alone. There are a lot of different ways to do this. There are a lot of different ways to approach this. But now knowing what you know about peaks and baselines in dopamine and understanding how important it is not just to achieve peaks, but to maintain that baseline at a healthy level, it should be straightforward for you to implement these intermittent schedules. For those of you that are begging for more specificity, we can give you a tool. One would be you can flip a coin before engaging in any of these types of activities and decide whether or not you are going to allow other dopamine supportive elements to go, for instance, into the gym with you. Are you going to listen to music or not? If you enjoy listening to music, well, then flip a coin. And if it comes up heads, bring the music in. If it comes up tails, don't. Okay. It sounds like you're undercutting your own progress, but actually you are serving your own progress, both short-term and long-term, by doing that. Now, the smartphone is a very interesting tool for dopamine in light of all this. It's extremely common nowadays to see people texting and doing selfies and communicating in various ways, listening to podcasts, listening to music, doing all sorts of things while they engage in other activities, or going to dinner and texting other people, or making plans, sharing information. That's all wonderful. It gives depth and richness and color to life. But it isn't just about our distracted nature when we're engaging with the phone. It's also a way of layering in dopamine. And it's no surprise that levels of depression and lack of motivation are really on the increase. Everything that we've talked about until now sets up an explanation or interpretation of why interacting with digital technology can potentially lead to disruptions or lowering in baseline levels of dopamine. I can use a personal example for this. I happen to really enjoy working out. I've always really enjoyed it. But in recent years, I noticed that if I was bringing my phone to my workouts, then not only was I a little bit more distracted and not focusing on what I was doing as much as I could have or should have, but also I started to lose interest in what I was doing. It wasn't as pleasurable. I would feel like it just didn't have the same kind of oomph, and I was beginning to question my motivation. As I started learning more about this relationship between the peaks and the baselines and dopamine, what I realized was that some time ago, I probably experienced an incredible increase in the amount of dopamine during one of my workouts because I enjoy working out and I enjoy listening to music. I also enjoy listening to podcasts. I also enjoy communicating with people. Those are all wonderful pursuits, but I had layered in too many of them too many times, and then it essentially wasn't working for me anymore. Much in the same way a drug wouldn't work for somebody who takes it repeatedly because their baseline of dopamine is dropping. So at least for this calendar year, I've made a rule for myself, which is I don't allow my phone into my workouts at all. No music, at least not from the phone. It can be in the room. I might listen to a podcast in the room, but I don't listen to anything or engage in anything on my phone, no texting whatsoever. And most of the time, I just don't even bring it with me for that period of time. It's only a short period of time. I'm not training that often. This is something that I think has been misinterpreted as people can't be alone now. People talk about, they can't walk across the street or they can't go anywhere, ride the bus, can't be on the plane without being in contact. They can't handle just their thoughts. I don't think that's really what's going on. I think what's happened is that we achieved the great dopamine increase that comes from this incredible thing, which I personally enjoy, being able to communicate by phone, by text, and exchange pictures and send links and these kinds of things, social media. But then what happens is it doesn't have that same fulfilling aspect to it. And it tends to remove the excitement and the pleasure of the very activities that we are engaged in. So I know this is a hard one for many people, but I do invite you to try removing multiple sources of dopamine release, or what used to be multiple sources of dopamine release, from activities that you want to continue to enjoy or that you want to enjoy more. And now you understand the biological mechanisms that would underlie a statement like that. It takes a little bit of working with. I know it can be challenging. In the first week or so of not engaging with the phone during any kind of workout, that actually was really tough. But now I'm back to a place where I enjoy it that much more. I also feel as if I conquered something in terms of the circuitry related to dopamine. I now understand why something that I enjoyed so much had become less pleasurable for me. And there's a deep, deep satisfaction that comes from understanding, okay, there wasn't anything wrong with me or what I was doing or anything at all. It was just there was something wrong with the approach I was taking, which was layering in all these sources of dopamine and dropping my baseline. For this very same reason, I caution people against using stimulants every time they study, or every time they work out, or every time that they do anything that they would like to continue to enjoy and be motivated at. There's one exception, which is caffeine, because as I mentioned before, if you like caffeine, that actually could be a good thing for your dopamine system because it does upregulate these D2, D3 receptors. So it actually makes whatever dopamine is released by that activity more accessible or more functional within the biochemistry and the pathways of your brain and body. However, a number of energy drinks and in particular pre-workouts contain things that are precursors to dopamine, and on their own, even if you didn't engage in the activity, would cause the release of dopamine to a substantial degree. They do cause the release of dopamine to a substantial degree. And over time, that will deplete your dopamine. So energy drinks, pre-workout drinks, drugs of various kinds that people take to study and pay attention. We talked about some of these for the ADHD episode, things like Adderall, Ritalin, armodafinil, modafinil, taken repeatedly over time will reduce the level of satisfaction and joy that you get from the activities you engage in while under the influence of those compounds. I'm not trying to demonize those compounds for their clinical use. What I'm saying is taking stimulants and then engaging in activities that you would like to continue to feel pleasurable is undercutting the process. And inevitably, it might not happen tomorrow, might not happen in a month, but inevitably you will have challenges with motivation and drive related to those activities. Now, some people can keep it right in check. They can just do the one can of the energy drink, or they only do their pre-workout before really hard days, for instance. More power to you. I actually do that sometimes, frankly. But people who are trying to get into that peak, super motivated, driven state, really focused every time they engage in an activity, you are absolutely undercutting the process and you are undermining your ability to stay motivated and focused. So just as we talked about intermittent reward schedules a moment ago, intermittent spiking of dopamine, if you do it at all, is definitely the way to go. And chronically trying to spike your dopamine in order to enhance your motivation, focus, and drive will absolutely undermine your motivation, focus, and drive in the long run. Ingestion of caffeine is somewhat of an exception among the other examples of things I've mentioned to avoid before what would otherwise be dopamine increasing activities. Because, again, caffeine can increase the density and the efficacy of these dopamine receptors. It turns out that the source of caffeine could also matter. While coffee or tea or other forms of caffeine will have this effect of increasing dopamine receptors, yerba mate, something I've talked about before on this podcast, has some interesting properties. First of all, it contains caffeine. It's also high in antioxidants. It also contains something called GLP-1, which is favorable for management of blood sugar levels. Yerba mate, it turns out, has also been shown to be neuroprotective specifically for dopaminergic neurons. Now, I should mention this is just a couple of studies, so we don't want to conclude too much from these studies. More needs to be done. But they showed that in a model of damage to dopamine neurons, ingestion of yerba mate and some of the compounds within yerba mate can actually serve to preserve the survival of dopamine neurons in both the movement-related pathway and the motivation pathway. So perhaps you need that incentive in order to ingest yerba mate tea. Perhaps you don't need any incentive. In my case, I don't need any incentive. I already enjoy yerba mate as my principal source of caffeine, although I do drink coffee as well. But if one were going to consume caffeine, you might consider consuming that caffeine in the form of yerba mate, both for sake of upregulating dopamine receptors and getting more of a dopamine increase, and of course for the stimulant properties of caffeine, if that's what you're seeking. And in addition to that, because yerba mate does appear to have some sort of neuroprotective, and in particular dopamine neuron protective properties. Now, that doesn't mean that caffeine is always beneficial, and actually there's one instance related to dopamine where caffeine can be particularly dangerous. And this relates to MDMA, so-called ecstasy. MDMA is under investigation in various clinical trials for its potential to treat trauma and depression. It's also, of course, a drug that's used recreationally. It's still illegal, at least in the United States. Whether or not MDMA is neurotoxic has been very controversial. Early on, it was thought that it is neurotoxic, that it can destroy serotonergic neurons. There were other papers that came out which argued that's not the case, and that's in particular because one of the early papers published in Science magazine claiming that MDMA was neurotoxic, that paper was retracted. It turns out that that study had mistakenly used methamphetamine instead, and methamphetamine is known to be neurotoxic. I think most of the data point to the idea that MDMA might not be neurotoxic, but in any case, caffeine has been shown to increase the toxicity of MDMA receptors. And you might say, well, how could that be? Well, now you understand why that could be. Caffeine increases the density and efficacy of these dopamine receptors, the D2 and D3 receptors. MDMA is a potent drug for increasing concentrations of dopamine as well as serotonin and other neuromodulators. And it appears that caffeine ingestion, by upregulating these receptors, can lead to more toxicity of MDMA. So caffeine can be a beneficial substance in one context and actually can be a detrimental, if not dangerous substance in another context. Two substances that greatly increase dopamine, namely amphetamine and cocaine, can cause long-term problems with the dopaminergic pathways. And this is largely based on a study.
Okay, let's start watching.
The following sections will explain what each one of the tools does and what is the best way to apply them, combine them, and the details of them in general. This is just for you to have a quick and high-level reference of our day-to-day process as data analysts, data managers, data scientists using Python. So the first data set that we're going to use is a CSV file that has this form. You can find it right here under the data directory. The data that we're going to be used is this. I have just transformed it into a spreadsheet so we can pretty much look at it from a more visual perspective. But remember, as we said in the introduction, as data analysts, we're not constantly looking at the data, right? We don't have a constant visual reference. We are more driven by the understanding of the data, right? In the back of our head, we understand what the data looks like, what's the shape of it, and that's what it's conducting.
Where can I access this stuff? Ah, here it is.
Our analysis. So the first thing we're going to do is we're going to read this CSV into Python, and you can see how simple it is. Just one line of code gets us the CSV read into Python. We're going to give a quick reference, and this is what the data frame that we have created looks like. Data frame is a special word, is a special data structure that we use in the Pandas tool. And again, we're going to see that in detail in the Pandas part of this tutorial. The data frame is pretty much the CSV representation, but it has a few more enforced things. Like, for example, each column has a strict data type, and we will not be able to change it, etc. It's a better way to conduct our analysis. The shape of our data frame tells us how many rows and how many columns we have. So you can imagine that with this amount of rows, it's not so simple to, again, follow a visual representation of it. It's pretty much infinite scrolling in this point. It's 100,000 rows. But the way we work is by immediately after we load our data, we want to find some sort of reference in the shape and the properties of the data that we're working with. And for that, we're going to do first an info to quickly understand the columns that we're working with. In this case, we have date, which is a datetime field. We have day, month, year, and that are just complementary to the date. We have the customer age, which is an integer, which makes sense, right? Age group, you can say it right here. It's age group, youth, customer gender. We have an idea, again, of the entire data set. We know the columns we have, but we also know how large it is. And we don't care what's in between. We will be cleaning it probably, but we don't need to actually start looking row per row, right? Just with our very limited eyes. We have a better understanding of the structure of our data in this way. And we're going one step further, we will also have a better understanding of the statistical properties of this data frame. With the describe method, for all those numeric fields, I can have an idea of the statistical properties of those. So for example, I know that the average age of this data set is 35 years old. I also know that the maximum age, in this case, if this is sales data, is 87 years old. I know the minimum is 17 years old. And again, I can start building, right, my understanding of the statistical properties of it. So in this case, the median of my age is very close to the mean. So this is telling me, all is telling me something, and the same thing is going to happen for each one of the columns that we are using. For example, we have a negative profit here, and we have very large values here. Are these correct? Is maybe this a mistake? Again, it's by having a quick statistical view of our data, we're going to be driving the process of analysis without the need of constantly looking at all the rows that we have. It's a more generalistic overview. So we're going to start with unit cost. Let's see what it looks like, and we're going to do describe only of unit cost, which is pretty much what we had right here. In this line, what we did was for the entire data frame, for the entire data. In this case, we're just focusing in the unit cost column. The mean, the median, all fields we know already, pretty much from this. And we're going to quickly plot them. We're going to use these tools to visualize them. And it's the same tool as Pandas that it's using on top, right? It's using Matplotlib. So the visualization is created with Matplotlib, but we're doing it directly from Pandas. And again, don't worry, this is all explained in the Pandas lessons. So this is unit cost, right? This is the box plot we have just created. We have the whiskers that shows us the first and third quartile, the median. And then we see all the outliers that we have right here. So we see that a product that is around $500 is considered to be an outlier. And the same thing if we do a density plot, right? So this is what it looks like. We're going to draw two more charts, right? In which we're going to pretty much point out the mean and the median, right? In the distribution chart. And we're going to do a quick histogram of the costs of our products. Moving forward, we're going to talk about age groups with the age of a customer. And at any moment, we can always do something like sales.head to give a quick reference. We know that the age of the customer is expressed in actual years old they were, but also they have been categorized with four age groups: seniors, youth, young adults, and adults, right? So we have given categories that were created, right, to better understand these groups, and we do that with value counts. We can quickly get a pie chart out of it, or we could get a bar chart out of it. As you can see right here, we're doing an analysis of our data. We see that adults right here are the largest group for our data, at least. So moving forward, what about the correlation analysis? What is the correlation between some of our properties? We will probably have high correlation, for example, between profit and unit cost, for example, or order quantity. That's kind of expected, but that's all something that we can do right here. This is a matrix, right, of correlation showing in red high correlation, so order quantity and unit cost, or where is profit right here? Profit is right here. So we see high correlation with unit, with cost, with profit. No, with profit. Actually, it's the opposite. Blue is high correlation. I'm sorry, the diagonal, which is blue, is correlation is equals 1. So high correlation is blue, and we see that profit has a lot of correlation, positive correlation with unit cost and unit price, and negative correlation is with dark red. So we again can have a quick idea. Let's see, for example, here profit, it has negative correlation with order quantity, which is interesting, right? It's we want to dig deeper into that. Of course, the profit has a high correlation positive with.
Are not very interesting.
So moving forward, something that we can quickly do when we're working with Python, especially with Pandas, is reshape our data or derive it from other columns, right? So this is pretty common in Excel. We can create these revenue per age column. If you're here in Google Spreadsheets, you're going to do something like revenue per age, and you're going to do something like equals, right? Equals revenue divided. I don't remember if this is the correct formula we're using, but just for you to have a reference. And we're going to pretty much extend this whole thing. There you go. Oh. Well, it's processing. I have 100,000 rows, so you can see how slow it is. And let's compare that just to the way Python works. I'm going to execute this thing. It was instant, extremely fast. And it was all calculated, so we have the same results as expected. And we can quickly plot both in a density plot and in a histogram, as you can see right there. Not that revenue per age is going to be relevant in any case. It's just to show you the capabilities of what we can do. Let's analyze. We're going to create a new column, which is calculated cost. And it's the total orders, the quantity of the order times the cost, right? Extremely simple formula, very fast to process. And we're going to get right here how many rows had a different value than what was provided by cost. So what we're doing right here is we're quickly checking if the cost provided by the data set at some point doesn't align with the actual cost we are calculating. So is there any mistakes that were made by the original system or people doing data entry? If this new column is different from cost, we want to know about that, and that doesn't happen. So again, quick regression plot. In this case, it's very obvious that there is some linear dependency between calculated cost and profit. So more formulas, in this case, cost plus profit. So we're going to adding a little bit more. There's no difference with revenue and the calculated revenue we are having, so that all makes sense. We're going to do a quick histogram of the revenue. We can, for example, add 3% to all the prices that we are using. We need to increase prices. How are you going to do that? Well, it's very simple with Python. We're just going to do increase everything by 0.03, and now all the prices have changed. What else? We're going to be able to do quick filtering. Let's get all the sales from the state of Kentucky, right? So these are all the sales from the state of Kentucky. We can get only the average of the sales by these age group on only revenue, right? So all these filtering options are extremely simple to get with Python. In this case, we say, give me all the sales from this age group and also from this country, right? And we're going to get the average revenue from this group that we are selecting. And again, to modify the data, we can make just a few quick modifications. Like in this case, we're going to say all the sales from country, right? The revenue, we're going to increase it by 1.1. I don't know why, we're just doing it arbitrarily. It's just for me to show you how it works. So far, so good. Again, we've done a couple things. You don't need to know about the details. We will actually go through that in the Numpy and the Pandas sections in this tutorial. So just for you to have a quick reference of it. There are exercises associated with this given lecture. So if you want to pause right now and get into the exercises, that's going to be very helpful. We're going to move forward now with the second lecture, in which we will be using a database, this Sql database, and we're going to be reading data instead of from a CSV file, as we did before. We're going to read data now from a database. Reading data from a Sql database is as simple as it is from an Excel file or a CSV file, as we were doing with our previous example. And once you've read the data, as we're going to do now, the process is the same. So what we have right here is a query, a SQL query. If you don't know about SQL, you can check our courses or other courses online. Basically, we're pulling the data from the database. This is one of the advantages of Python. It's that there are connectors for pretty much every database provided out there: Oracle, Postgres, MySQL, SQL Server, etc. In this particular example, we're going to be using MySQL. So once you construct a query and you pull the data from the database, then the process is the same. We have just converted this outside data into a data frame that we can use with our Python skills. The first step, as usual, is to check the shape information description of our data frame. In this case, we want to again understand the structure of it. So we want to know how many rows we have, 16,000. We want to know a little bit more about our rows. We want to know a little bit more about our columns and how many rows, how many records we have for each one of them, and the type of each one of these columns. And we also want to have a better statistical understanding of our data. So we do a quick describe and we have more details about it. If we want to focus in individual columns, right, we can just do that by, in this case, we're going to focus in film rental rate, right? Pretty much how much you pay to rent a film. And we're going to see the kind of distribution we have. We can call it distribution. It's pretty much a categorical field in this case, but basically the rentals are divided in three main categories or prices: 0.99, 2.99, 4.99. So that's this box plot is pretty much perfect. Never seen in real life box plot gives you those prices. And moving forward, we can also check very quickly a categorical analysis, understanding the distribution of rentals between cities. So we have two cities, and it's pretty much even, as you can see right here. Creating new columns and reshaping the data for further analysis, etc., is relatively simple. In this case, we're going to analyze the return in rentals, right? Which films are going to be more profitable for the company? Dividing the rental rate, how much we charge, divided by the cost, how much it costs us to acquire the film. So in this case, we can see the distribution of that, right? So most rentals are here in the beginning, and then we have more profitable rentals. We're making up to 60% above the rental, and we can quickly analyze the mean and the median of it, right? So to have a quick idea of all that. Finally, selection and indexing. If you want to start focusing, if you want to go in the data, right, you want to zoom in, you want to have a better understanding, so you start filtering. In this case, we can filter by customer, but if you want to do it per city, if you want to do it per state, if you want to do it per film, per price category, etc., it's very simple to filter and zoom in just one particular characteristic of your data, so you can perform a more detailed analysis. So in this case, we have all the films that were rented by the customer last name Hansen, which doesn't mean it's the same person, but again, it's very simple to filter that. And here we can very quickly see which ones are the films, that have the highest replacement cost, right? So basically what we're doing is we're going to isolate those films that have the highest replacement cost. And also we can see right here, just for you to have an idea, all the films that are in the category PG or PG-13. It's very simple also to filter that data. So this is the process we usually follow. We import the data, we reshape it somehow, create columns. There is an important process of cleaning that we're not highlighting this part of the tutorial. We're going to talk about it in the tutorial itself. There's the process of cleaning, then reshaping, creating new columns, combining data, and creating visualizations. This is the process, right, that we're following here with our Python skills. There's a ton more to add, as you might imagine, from creating reports to running machine learning processes, creating linear regressions, etc. For now, this is just a quick understanding of the process we follow. And now, starting now, we're going to move forward with more details of each one of the individual tools. We're going to talk about Jupyter Notebooks. We're going to talk about Numpy. We're going to talk about Pandas. We're going to talk about Matplotlib, Seaborn, etc. Starting now, right? The first thing you're going to see is what is this whole thing that I've been using, this Jupyter Notebook. I want you now to, if you don't have experience with it, I want you to have an idea of how it works, and then we're going to move forward with the individual tools, Numpy, Pandas, etc. Remember, there are exercises also associated with this particular lecture, so you can. Before we jump into the actual data analysis course and we start talking about Python, Pandas, all the tools we're going to use, import files, read data from databases, etc., I want to show you the environment that we work with. It's our primary environment. It's the tool that we use 99% of the time, and it's Jupyter Notebook. There are going to be different terms here. I'm going to be referring to it as Jupyter Notebook, but as you're going to see in this part of our tutorial, you're going to see that Jupyter is actually a whole ecosystem of tools, and it's a very interesting project. Jupyter is a free and open source, again, ecosystem of multiple tools, and primarily we're going to talk about first what is a Jupyter Notebook, which you're seeing right here, and you're going to see live in a second. I can actually show it to you, is this thing we're going to use. And we are also going to talk about Jupyter Lab, okay, which is the evolution of the regular Jupyter Notebook. So I think this could be familiar to you already. Usually the question is, what's the difference between Jupyter Notebook and Jupyter Lab? Well, the difference is that Jupyter Lab is just a nicer interface on top of Jupyter Notebooks. It's not just the plain notebook. This is a notebook when I'm scrolling right now. It's also the addition of a tree view. It's an addition of Git tools, and it's an addition of command palette and multiple other things. You can open some files with a nice preview in it, etc. So Jupyter Lab, Jupyter Notebook, they are similar. Jupyter Lab is, again, the evolution of a Jupyter Notebook, and that's what we're using. Again, Jupyter is a free and open source project, so anybody can install it, anybody can download it. It's very simple to get it set up in your local computer. In this case, we're using something we call Notebooks AI. It's a project that provides Jupyter environments for free in the cloud, so you don't need to install things locally. You don't need to put things in sync in your own hard drive, right? That means you don't need to buck it up, for example, because it's just a service and it's all works in the cloud. So said that, I want to tell you that we have compiled a very quick list of everything we're going to talk in this part of the tutorial. In this list of tweets, just a thread with multiple hints of how to use Jupyter Notebooks. So after the video, after the course, if you forget some of these concepts, you can always go back to this tweet. It's a quick reference for you to have. So let's get started. Why do we use a Jupyter Notebook? Because it's an interactive, real-time environment to produce to explore our data and to do our data analysis. It's a tool you're going to fire commands and it will immediately respond with something back. It's a very interactive tool. When we're working with data analysis, and this is mainly the main difference with some other tools, like for example Excel, Tableau, etc., is that we are not constantly looking at the data. There is no visual reference, like for example you have in Excel, right? So in Excel, you're constantly looking at the data. You have it in front of you. There are 100,000 cells, and you can scroll and see them. The problem is that that's not scalable, right? It's like nobody can work with 100,000 rows in their mind. We will always forget something. So the way we work with Python in data analysis is by always having a reference of how our data looks like, but always at the back of our head. We're not constantly looking at it. We're like this person from the Matrix, you know, the commander of the Matrix that commands people to get in and out. We're basically basically asking data, right? Asking questions to the data and having a picture in our mind of how that's going to work. We're not constantly looking at it. We're just having a reference in the back of our heads of what our data looks like. So that's why this tool is very useful. This tool is useful also if you're just training your Python skills and other programming language skills, because what you're going to see is that it's just a regular Python interpreter. In this case, I can execute some code that's do 1 plus 3. There you go. And the result is 4, right? So this is a Python. Is a fully featured Python interpreter. The good thing is that, again, it's going to respond to us pretty much immediately. I create a command, and I immediately get a response. I can do something like print here, hello world, and I immediately get a response. I can do hello world times 3. Again, it's again a Python interpreter, a fully featured Python interpreter, but it's not being accessed from a terminal, which you can, right? This is the good thing about Jupyter Lab too. You have a terminal. I can do Python, right? And I can do 2 times 3, and I get an answer back. But this is not convenient to work with our data. We need something a little bit more interactive. We can also mix with documents. That's going to be the advantage of a Jupyter Notebook. So what's the way we work with Jupyter Notebooks? There are a few concepts, very important concepts, that we are going to follow. A Jupyter Notebook is just a sequence of multiple cells. Okay, everything is a cell. And as you can see, when I click on these cells, even if it doesn't look like being a cell, it is. You will see that this blue thing right here, right, is pretty much following me because I'm clicking on the cell and I'm selecting that particular cell. Everything happens within a cell. If I want to execute some code, I can do again 1 plus 5, and I get a result back, right? That's how it works. So I'm creating a cell. I'm deleting a cell. I create another cell again. So everything happens with a cell. And I'm going to tell you how to add the cells, how to remove them, how to execute code, etc. The interesting thing about a cell is that it can either be Python code or any other programming language you're using. In this case, is a Python data analysis course. It can be Python code, as we were doing before, 1 plus 3. This is Python code, or it can be what we call Markdown, okay, which is a format, right, to create text that will be rendered with sort of HTML at the output. So in this case, this is what the source code of the Markdown looks like. In Markdown, any line that starts with this paths, it's going to be a title. In this case, it's going to be the biggest title you can have is just one pad, and then you keep adding to reduce the size. In this case, a level 3 title. And then you can have, for example, this is a quote, this is bold, this is italics, this is a link, right? So I could copy the cell and open the source code. There we go. So this is a link, right? Issue is created, or it's rendered as a link. So Markdown, what is a text formatting tool, right? Or protocol, we could say. That in this case, we just specify, we have some rules to use in our text, and Markdown knows how to interpret them and format, right, or return a formatted document after them. So for example, here we have green divider, which is a picture, and we know it's a picture because it starts with an exclamation mark, and that's what you're saying right here. So again, a cell can be either Python code or it can be Markdown. Markdown is an entire thing on its own. You can get any tutorial online free. It's fairly simple to get started with. And it's also very important because when you're formatting your reports, right, when you're creating your reports, you want them to look pretty, you can use Markdown for that. And what we're going to see later is that you can export these notebooks and they will generate PDFs, right? So this whole thing can be a PDF or an HTML page. So after you're done with your data analysis, you can hand over to whoever asked for the analysis a PDF report, which is pretty neat. So moving forward, again, any cell is going to be either Markdown or it's going to be code right here. So this one's code. And you can switch the modes. You can say this cell's code, or actually let's make it Markdown. So right now, if it's a code, it doesn't matter at all. Right? It's not executing anything because the cell is interpreted as Markdown. So now I'm switched back to code, and now it works again as it should. It can also be raw, but to be honest, we don't use raw very often. So again, you have this general cell type. This cell we're using, what type is it? Is it code? Is it Markdown? You can switch it with this selector right here. So a few more things that I have to tell you right away so you can start internalizing them. And it's going to take some time to get used to it, but once you get used to it, you're going to move very fast in your data analysis with Python and Jupyter Notebooks. The first thing is that, as you're saying right here, every cell has been given an execution number. So the cells will be moved, right? They will be moving around. You will be moving them around, but you will always know which one executed before another one. And that's because every execution you run will be assigned an execution number. In this case, this is the 7th time I have executed code. If I execute code again, for example, I don't know, 2 times 2, this is the 8th time that I've executed code. And if I move this thing, right here, if you're reading this thing top down, you will not be fooled, right? You will understand that this thing, it was moved. The cell was moved. The structure of the notebook changed. But this thing was executed after this other cell, right? This is 8 and this is 7. So the execution order is always preserved. So that's an important thing. Something else that you're saying me change the structure and do things with the notebook without using any menu. And that's because I know how to use keyboard commands, keyboard shortcuts to run most of these commands. So, for example, how can I add a new cell? I have, this is a Markdown cell, and this is a code cell. If I need a cell before this one, what's that command that I'm going to issue in order to create the cell? In this case, the command is going to be the letter A. I just type A, and there is a new cell created. How can I delete the cell? It can be 2 times the D key. 2 times the D key. And again, this is all in this reference we built. So, for example, right here, where is it? At some point, you can... here you can press A to create a new cell. You can press B to create a new cell, what we call below. So let me put something here. This is a reference. And I'm going to put here the letter B. It's going to create a cell below the currently selected one. So the selection here is here in the blue. Let me delete this one. I hit B, and it's going to create a cell below the previously selected one. If I hit A, it's going to create a cell above the previously created one. So these are the mnemonics of the creation. Something else that is very important. Why, when I'm in this cell and I hit the letter A, literally I just hit the letter A in my keyboard, no control, no command, just A, it creates a new cell and it doesn't type A inside the document, right? So right here, if I type A, it's adding an actual A character in the cell. Why didn't that happen before? And you're going to notice that when I change what I'm going to call a mode in a second, you're going to see that the content of the cell is grayed out. So now when I press on the letter A, it actually creates the cell, and it's not adding content to the cell itself. If I go back again to the other mode, and I'm going to give you a better explanation in a second, if I type anything, in this case A, it's actually appended to the text within it. So this is my introduction to cell modes, and this is very important. The Jupyter Notebook is a mode-based editor, right? So there are multiple editors, or for example, Vim or VI, those are mode-based editors, which basically the behavior of your work will change depending on the mode that it's currently activated. So for example, in this case, I am in edition mode because any character that I A is going to create a new cell above. B is going to create a new cell below. Double D is going to delete the cell, right? So that's the important part of that's one of the most important parts in order to understand how to work with Jupyter Notebooks. The mode that you're currently working with. And there are only 2 modes, so it's fairly simple. This is command mode, and we recognize command mode because the cell is grayed out. When we get into edit mode, there is a regular prompt, as you are seeing before. To edit mode, you're going to hit the return key, and that's going to get you into edit mode again. So we have tackled multiple things already. Switch it out of editing back to command mode. And if you actually want to make modifications to the cell, basically you want to get into edit mode, you're going to hit the return key. And that's going to get you into edit mode again. So we have tackled multiple things already. Again, we said in Jupyter Notebooks, we're going to use Python code very quickly to interact with our data. We need a real time, I'm asking, you are answering type of editor. That's what the Jupyter Notebook is. The Jupyter Notebook has these 2 modes, edit and command mode. And then the cells, which is pretty much everything. It's a fundamental part of the notebook, the cell. It's going to have 2 types. It's going to be either code or it's going to be Markdown, right? And now I'm going to start showing you more features, and I'm going to show you the most important commands, and of course what the keyword shortcuts for those commands are, so you can move freely and work with Jupyter Notebooks in the most efficient way. So let's get started. First of all, from the most important commands is moving, right? So navigating. It's very simple to navigate. Just use your arrow keys up and down, and you're going to move around in your notebook. If you wanted to switch the type, right, going from Markdown to code, etc., you can use these drop down, or you can press the specific keys to switch to either Markdown or Python. So for Markdown, you're going to hit the M key. That's going to make it Markdown. For Python, you're going to hit the Y key. That's going to make it Python code. So M and Y are going to switch you back and forth. Keep an eye on the selector. I'm going to hit Y, M, Y, M. It's going to switch it from code to Markdown. What else? How can you execute code? Once you are within your typing code and you want to execute it, there are 2 types of executions you can run. The first one is going to keep the selection, the currently selected and active cell, is going to stay at the same place you are. And that's going to be by keeping pressed the control key and hitting return. So that's going to run the code, and the prompt or the current selected cell will remain being the same. So I'm running this thing a couple of times already, and the selection or the currently highlighted cell stays the same. I can change that by using shift return. So I keep the shift key pressed and I hit return, and it's going to execute the code, but it will immediately switch the prompt or the currently selected cell to the following one. And that's useful when you have multiple cells you want to execute one bit after the other. So you can keep hitting shift return, 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 and it keeps you moving right from top to bottom. All right. So control return or shift return to change. The execution is the same. It's just what's going to happen with the currently selected cell. We already saw how to create cells. With the A key, we create a cell above. With the B key, we create a cell below. To delete a cell, you're going to hit the D key, 2 times, one after the other, very quickly. DD is going to delete the cell. What happens if you made a mistake and you want to undo the previously issued command? Well, the mnemonic here is going to be Control Z. You know, the mnemonic, it's not the command, it's going to be Control Z. You only need to press the Z key. You don't need Control, just Z, and it's going to undo whatever you did in your previous command. All right, so A, B, D, deletion, and then Z to undo. All the commands we're seeing, they all have a correspondence in this toolbar or in this command palette. So for example, right here, I could run this code by pressing this play button. Right here, you see it, that the execution is changing. There are multiple ones, and you can search them if you don't remember right here. And the neat thing about it is that you actually have the shortcuts to issue the same command. So let's say you don't remember how execute and stay in the same cell, or move, whatever. You can search for run, and you can see what's the name and what's the actual command that you have right there, right? So you can, at least for your first, I don't know, month working with Jupyter Notebooks, you will usually need to go back to these commands and try to remember the quick shortcuts, and with time and practice, those will just come naturally. So moving forward, what else? We have a few other commands. In this case, we have moving forward, we're going to use some code here. We're going to import some tools so you can see some characteristics or advantages of Jupyter Notebooks and why we use it so often compared to, for example, the regular Python terminal. One very important thing is visualizations. We, as data analysts, we're constantly getting data and expressing it through images or animations, right? But most commonly images. The main library we use in Python is matplotlib, and matplotlib is a first-class citizen in Jupyter Notebooks, which means that you can just run the figures from matplotlib and they will just show up directly in your notebook without the need of doing anything crazy. So can you imagine showing this beautiful picture in this terminal? That's very hard, of course. So again, that's one of the main advantages.
Right back.
advantages of a Jupyter notebook. Moving forward, what we're going to do is we're gonna get some data from a public API. So there is this CryptoWatch service, which basically has crypto information, Bitcoin, Ether, etc. And you can check the docs. We can actually open them. It's gonna give you market data, etc. You can check the docs and how you can get, in this case, it's BTC, Bitcoin to Euro. Let's actually see if we can change it to USD price. There you go. So this is the current price of Bitcoin, results, price, etc. And we're actually gonna do markets. Do we have Kraken, BTC? And let's actually issue the same query we're going to use, which is open, high, low, close, OHLC. And don't worry, this looks ugly, but this is actually what we're using. This is a list of results, right, for all the different candles, we call them. We get the idea of the open price, close price, high price, and low price. So we're going to issue these requests to the internet, to this API, the CryptoWatch API, so we can get information about Bitcoin to do some analysis. I say Bitcoin, you can actually get it from Ether, for Ether, for all other different types of crypto or currencies. So the function we're defining is get historic price. It's a very simple function that uses Pandas, one of the most important tools we're going to be using in this course, and the requests library, which is also a very famous library for Python. And what we're going to do here is we're going to get Bitcoin and Ether price for an entire week, right? So from February the 25th up to today, right? So depending on when I'm shooting this video. And we're going to get a quick reference of the prices, open, high, low, close. So in this case, we have for information per hour. Okay, so this is something you can actually change in the request you're making to the API. You can reduce the candle size. In this case, we're keeping it per hour. So we have by the hour information about Bitcoin in this particular market, which is Bitstamp. Here we have this day, and this hour, right? 1 a.m. in the morning, open, close, highest price and lowest price, and also the volume that was operated within this time period. And we're going to immediately plot the price. So we see that in this time, which I think is an entire day, the price dropped. It's actually a few days, like an entire week. The price dropped from $9,600 below, right, 9,000. So it was a pretty significant drop. Let's see Ether, how it performed. We have here all the records and how it moved. So this is what I told you, that when you're doing data analysis with a programming tool like Python or R, you're not constantly looking at the data. So what I'm showing you right here are the first 5 records. We actually have, let's do that. We actually have 169 records, okay, 169 records. And this is per hour, so if we do 169 hours divided by 24 hours, we have 7 days, right? So we have 7 days of data. 169 records, and then we have a little bit more information here, statistical. I'm going to get to that in a second. But basically, this is what I'm telling you. 169 records, to be honest, something you could be seeing in a spreadsheet, but I want you to get the concept here. We're not just looking at our data. We have it in our brain. We know what it is. We know what shape it has. We know how many records it had. We know information, what's the standard deviation, what's the mean of that, right? So close price, what's the standard deviation, right? What's the average, the mean, the median, right? So we have information about our data. It's sitting behind, in our brain, but we're not looking at it. And that's because it's a very simple example with only 169 records, but in real life, we're dealing with millions of records. So it's impossible to see it. Have you ever tried scrolling in an Excel spreadsheet through millions of records? It's crazy. It's not possible. It's just unusable. So that's, again, the way we work with data analysis in Python and R and other tools. We don't constantly keep an eye on the data. We know the shape of it, and we just have these quick references, like show me the first 5 records, show me the last 5 records, show me this chunk here, that, there, but that's it. So again, these are the visualizations we're creating, and Jupyter Notebooks, again, it's just very simple to get the plot done right there. We're going to also see in Jupyter Notebooks a few other pretty neat things. The first one is that we can use another library which is called Bokeh, and the difference is that Bokeh will have charts that are interactive. So I'm moving it right here. It has JavaScript and it's interactive. If you look back again to what we had here, this is a static chart. It's just a PNG. You can actually export it as a PNG. There is nothing you can do with it. With Bokeh, it's actually dynamically generated interactive chart. So I can zoom in piece of data, right? I can move it around. I can just do whatever I want with it. I can refresh and reset it to whatever it was, and it's a dynamically generated chart. The difference is if you're working with data dynamically in your analysis, sort of in your exploration, then Bokeh is a pretty neat tool because you can zoom in, right? So what's going on here? Let's look at this thing. If we're working on a mean reverting strategy, for example, we see a high value, we see a low value, the mean is going to be here, so we see some mean reversion in there. It's very interesting. If you need to, for example, export a PDF, export a huge HTML file, then static images are going to be probably better. So that's the difference between them. To be honest, Matplotlib is a lot more popular than Bokeh. We use Matplotlib a lot more because we actually have a few other tools like Seaborn that make it very easy to access and use it. What else? Jupyter Notebooks work very well with some Excel files, with other file formats, CSVs, XMLs, Excel files, etc. And that's also the availability of Jupyter Lab. So Jupyter Lab can immediately interpret and open CSV files. It can open with some extensions XLS files, XML files, JSON files, has a very nice editor and tree view for JSON. So the Jupyter Lab environment combined with Python Jupyter Notebooks will give you a good idea of Jupyter in general. So in this case, we have just saved, I'm not going to execute this, you can try it out, but you can execute and run what we have just done and export this crypto file as an Excel spreadsheet. So you can just click on here and you can basically download it. I'm going to open it and see what it has. There you go. So let me reduce the size of this thing. There you go. So you can see that we have just exported two sheets, in this case Bitcoin and Ether, right, with the data that we had in our previous notebook, right? So that's all, again, the combination of Jupyter, the combination of Python, the combination of Jupyter Lab, which our tools just work very well together. So we're going to keep moving forward in this video, this tutorial, talking about more data analysis in general. We're going to talk about Python. We're going to do a quick review of Python. Maybe when I was running these commands, you felt a little bit lost what I was doing with it. So we're going to do a quick review of Python and all that. And of course, we're going to get directly deep into data analysis with Pandas, with some other tools. I want to tell you something before we finish this chapter, and it's that it's very important for you to get familiar with data analysis, with Jupyter Notebooks, because you're going to spend a ton of time with it, and it's a very, very valuable skill you can get if you get proficient, comfortable with Jupyter Notebooks, like creating cells, deleting cells, cutting, pasting, moving things around, etc. For you to generate reports, Jupyter Notebooks are going to be excellent. So keep an eye on it, keep practicing it. The only way to learn it, to be honest, is keep practicing it, keep open the command palette, so you can always, if you forgot, how can you cut a cell? Well, there's here this command X, right? It's going to just tell you up front. Keep an eye on it, keep working with it and practicing it. And once you get familiar with Jupyter Notebooks, you're going to move very, very fast. Remember, we have these nice list of compile commands and reference you can always access if you need extra help. And we're going to keep moving forward now with more data analysis.
20% already.
And now it's time to talk about NumPy, one of the most important libraries in the Python ecosystem for data processing in general. It's the one that got pretty much everything started, and if you trace back NumPy, it's a very old developed library, 20 years maybe. It's an extremely popular library and an important library. I'm not going to say popular, and I'm going to explain why in just a second, but it's a very, very important library in the Python ecosystem for data processing. NumPy is a library that will let you, it's a numeric computing library. It's just to process numbers, to calculate things with numbers, and that's it. So NumPy has a very limited scope, we could say, and this is on purpose, a very simple library when you look at it and when you look at the API, which is very consistent, by the way. Why is NumPy so important? Well, in Python, numeric processing, in just pure Python, processing numbers is very slow. Okay, Python is not slow as itself compared to other programming languages, but when you go down, right, to very deep levels of performance, when you are processing large amounts of data, right, and you need to squeeze even that tiny byte at the end of your pipeline, you need to squeeze every flop from your CPU, then Python is not the right tool for that. Python as a pure Python programming language. NumPy is actually solving that. NumPy is a very efficient numeric processing library that sits on top of Python and gives you the same API as you're going to work with just writing Python code, as you're saying here, but low level. It's going to be using high performant numeric computations and arrays and numbers and representations, etc. That's it for NumPy. It's extremely simple from an API perspective, but it's extremely powerful. Why did I say that it's not so popular, but yes, it's so important? Well, because in reality, we don't usually employ NumPy directly. You will not see yourself using NumPy so often, but you will be using other tools in Python, like for example Pandas and Matplotlib, and they are all working on top of NumPy. They're all relying on NumPy for their numeric processing. So that's why NumPy is so important. So at least for this part of the tutorial, NumPy, I'm going to divide it in two pieces. The first one is going to be a very detailed, low-level explanation of how NumPy works, why we need to use NumPy, and what are the differences between different byte sizes for numbers. We're going to talk about integers, but this is going to apply for decimals and date times also, and why you need a very low-level optimized tool as NumPy. Now, you can skip this part. You're going to find in the description of this tutorial the precise moment in time, so you can just skip and go directly to the second part, which is when we actually start using NumPy, and I show you how to create arrays, how to make computations, etc. So for now, we're going to divide it in two parts. We're going to start first with the low-level explanation, which you can skip if you want, because it's not going to be crucial. You can easily use NumPy without it. We found that for some of our students, it's important to understand the low-level basics of it, especially if you didn't have a computer science background. It can help you get, raise your level of understanding of computers and how to make your computations more efficient. But don't worry, if you don't want to go through that now, it's fine. You can skip this part and come back later or at any other moment. You don't need these to use NumPy. Seriously, you don't need it. It's going to be beneficial, but you don't absolutely need it, so you can just skip and come later. So with that said, let's actually go into a deep understanding and explanation of how computers store integers, numbers in memory, and what are bytes, bits, etc. In order to understand why NumPy is so important, we have to go back again to the basics. What are numbers? How they are represented in computers, etc. As you might know already, a computer can only process ones and zeros, bits. It can't process numbers, or just decimal numbers to be more correct, sorry. It only can process ones and zeros. A computer is just always storing and processing ones and zeros. It's a binary machine. your memory is the central place, the RAM, the random access memory in your computer, is the central place where your computer is storing the data that it's actively processing, right? So you have, for example, a hard drive, which stores long-term data, but the computer can't process data directly from the hard drive. Before doing that, it has to load it into your RAM, into your random access memory again. Usually, right, a computer is going to have, what, 8 gigabytes, 16, 32, it doesn't matter. Let's say you have 8 gigabytes of memory. That, at some point, is going to translate to number of bits that your computer can store. So if you follow these, we have right here, you can see the total number of bits available in a regular computer with 8.
I don't like how this guy, he just stalls too much.
Memory for the same data, and also how to make it faster, right, for your calculations. So in terms of physical storage, or actually memory storage, right, how can we make it, how can we optimize to use the least amount of memory for this given problem? That's the objective of optimizing it. We need to understand how numbers, decimals, or sorry, integers in the decimal numeric system are represented in binary, right? So this table right here shows you the first 9 numbers, 0, 1, 2, 3, 4, etc., and their binary representation. In your computer, let's say you want to store the age of a user, which is, I don't know, 32. You can't store 32 in here because your computer, again, doesn't know about decimals. It only knows about binary. To do that, you will need to find the correct representation in ones and zeros of 2, which is not this one, to be honest. I'm just making it up as we go. But again, you need to know the correct binary representation of this number in order to store that data. How can you know that? Well, there is this whole binary arithmetic, right? There's a whole part of math dedicated to binary. Doesn't matter for now, but I'm going to just drive the intuition of it so you can have a better understanding, and if you're interested, you can dig deeper later. So basically, any decimal number needs to be stored in a binary format, which of course only takes ones and zeros. And what we usually do is just we keep increasing zeros and ones in positions, right? So in this case, we have the number 0, the number 1, that's fine. Once we need to store the number 2, we need now to increase the number, the position right here. We need to increase, right? We need to go from 2 to 1, 0. We go to the number 3, it's 1, 1. And then when we need to go to number 4, we need to increase positions again, because we only have 2 symbols, 0 and 1. So as you're seeing right here, up to this level, we need only 1 position. Up to this level, we need 2 positions. This level, we need 3 positions. And this level is going to need 4 positions. And you see how the size of these is increasing, and it has an explanation behind it that we're going to see in a second. So the question is how many decimal numbers you can store with bits. So let's say we have n bits, and let's say n is equals to 3. That means that you only have 3 positions, right? 3 bits. How many total decimal numbers you can store with it? Well, we can store 0, 0, 0. We can store 0, we can store 1, 0, 0. We can store 1, 0, right? So in this size, we can store up to here. We can store up to 7 numbers. 1, 1, 1 is equals to 7. Once we've filled all the positions, right, we've reached the limit, right, the largest number, the largest binary for this amount of symbols or positions. That's the number 7. So this means that with 3 numbers, you can store from 0, here 0, up to 1, 1, 1. In total, you can store 8 decimal numbers. Here you have 8 decimal numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8 total decimal numbers from 0 to 7. The equation, if you want, behind this is as follows. If you have n equals 3 in bits, in order to know how many decimal numbers you can store with those bits, it's 2 to the power of n. In this case, is total 8 bits. So if we go back into our drawings, we said that with 3 bits, we can store up to 8 decimal numbers. And again, the equation is 2 to the power of n. It's going to give you how many decimal numbers you need. You can always do the opposite process using the logarithm and get how many bits you're going to need to create to store a given decimal number. I'm not going to get into that, so we don't complicate it. But again, the math behind it is extremely simple. So now, moving forward, we're going to delete this whole thing. Moving forward, why is this important? When you're working with your data, when you're doing your data analysis, you know what type of data you're working with. They're all numbers, but numbers usually have a connotation behind, right? So let's say that you have here, it's a table of people, and you have the total net worth of the person, and also you have the age of the person. The age is a value that will range between what, 0, right, just 1, to, I don't know, 120, we can say. I don't know what's the maximum age registered right now, the oldest human being. But 0 to 120, it seems reasonable. In your other column, net worth for this person, the range it's completely different. We can go from something like $0 up to, I don't know, $60 billion, I think, Mark Zuckerberg or Jeff Bezos or one of those. So we go from 0 to 60 billion. In this case, if they're dollars, what happens if this is a highly devaluated currency? We have to go to trillions, right? So these two, even though they're just plain numbers, and we can say they're integers, even though these are plain numbers, they have integers, they have a different connotation, and they will need different requirements in terms of storage size, right? So if we say that an age goes from 0 to 120, we don't need so many bits to store it in memory, right? We can do the math actually. How many bits do we need in order to store 120, what do we say? 120, right? Well, if you do the math, you will see that 2 to the power of 7 is 128. So if you have 7 bits here, 7 bits, you're gonna store from 0 up to 1, which is actually 127. Okay, these number, all ones, 7 ones in binary, is equals to 127 in decimal. In total, we can store 128 numbers, 0 matters, up to 127. So that means that for our column, right, the column age here, age, we can use the size of the memory we need to use is going to be 7 bits per user, or customer, or person, whatever. What about these number right here? If we have to go up to a couple billions, well, in that case, the number is a little bit more complicated. We're going to need, for example, we can say 64 or 32. 32, it's actually 64 probably, but with 32 bits, right, you can store up to from 0 up to this value. So again, I don't know about the currency we're using or anything, so we can assume that here we need 32 bits in order to store that. And now you can do the math. How much memory space you need in order to process this data? How many records do you have? If you have only 1,000 records, that's not significant. You can use whatever. You can use 64 bits here to store the age, and you're not going to have a problem. But what happens if you have more? What happens if you have the entire population of the Earth? You have 7 billion records here, 7 billion records. Then every bit that you're saving in these columns is going to be important because it's going to take a ton of data. And of course, you have a ton more columns, right? What happens if you're processing trillions of records from financial transactions, right? You want to be very efficient and optimize every single bit you have, and that means again selecting the correct number of a bit per the column you're currently processing. So far so good. Again, we understand that the number in decimal we need to store has a correspondence in bits, right? 8 bits is 1 byte, and the more we can optimize that, the less memory we're going to use for our applications. Where does NumPy come in place? Why are we talking about this in this NumPy lesson? Well, the idea is that NumPy is a library that will let you, has a very advanced numeric processing in order to let you select the number of bits that you want to take for an integer. Even more, let's say you forget about NumPy, you want to process this thing with pure Python. So you do x equals 5, for example. You're working with Python, you create a number. We're storing age, and say 5. How many bytes, how many bits do you think this simple variable takes in memory? How many? Well, in reality, even though we think it should be around, what, 3 bits? 8, let's say, to be too simplistic. In reality, for Python, this is going to take around 20 bytes. Okay, so we are wasting a ton of memory in order to store this number. And why is that? Well, because Python is a high-level object-oriented programming language. The reasoning behind it is that Python is simple to write, all right? Simple to also read and code on top of it. But again, in order to create that simplicity, it needs to wrap all the numbers in objects, which have all these attributes that if you know advanced Python, you're going to recognize that are not necessary. So these is taking a ton of memory, and a regular, very simple number in Python ends up consuming 100 times more memory than what it should be consuming. And this is when NumPy comes in place. In NumPy, you can create numbers that are, for example, you can control the size in terms of bits. You can say, I want to create a number that has only 8 bits. And that's it. That you're going to create a 1 byte integer, and you're very precise on how much memory it takes. You can create a number that it's, actually I need a little bit more space. So I'm going to do np int, and we can here use the tab key. You're going to get auto-completion, 16 bits, or 8, or 32, or 64, right? So we can actually be a lot more precise in the number of bits that we need. And this is extremely important for, again, our high-level processing. On top of that, NumPy is an array processing library. NumPy is 99% about processing arrays, constantly processing arrays. The data structures we have in Python, the built-in data structures we have in Python, for example, the list, the dictionary, they're not optimized for high-level computing. So if you have a list of numbers in Python, let's say you have, I don't know, L equals 3, 2, 2, 4. Right? You have 3 numbers in your list. In Python, it's not guaranteed that the list is going to contain all the numbers at 3, 2, 4 in contiguous positions. It might put them in separate positions in memory. On top of that, you can't rely on advanced CPU directives and instructions for processing matrices, because Python, again, is wrapping these things in objects, so there is no access to these high-performant, low-level instructions. With NumPy, that changes, because when you create an array in NumPy, you say, I want to create an array of 3 numbers, and they're all int 8. Then in position, forget about this. These are not bytes. I'm using this drawing as a general representation of memory. So in that case, in NumPy, when you create this 3-element int 8 array, it's going to create those 3 elements in contiguous positions in memory, 3 to 4, and they're only going to take that amount of memory that we said they were going to take. And on top of that, we can rely on a bunch of very efficient low-level instructions from your CPU for matrix calculations. This is something that is a little bit more advanced, and it's something that has exploded in the past 10 years. CPUs with richer instruction sets, and the same thing for GPUs. You might have heard, especially with machine learning and all that. We need fast array processing when we are storing features and weights and all that. A topic for a different tutorial. But again, the idea is we need, right, a ton of, we can use all these important and very efficient low-level directives from our CPU, which makes our computations a lot faster. So again, as a recap, you don't need to know all these to work with NumPy. That's the first thing. Second, you don't need to get extremely So with that said, we're going to see now how we actually use NumPy without worrying so much about the low-level details, and that's the beauty of NumPy. So we have already done our low-level explanation of binary, arithmetic, why NumPy is important and all that. If you skipped it, that's perfectly fine. You will not need it. The reasoning was to include it was that if you're in this tutorial, you're probably looking for fast and efficient options to process large volumes of data, and that's when all those things come into play. So without further ado, let's just get started and start using NumPy as a library. So again, as I told you, NumPy is a very simple library for array processing and numeric processing. It has a few objects, numbers, floats, integer floats, arrays, and that's it. And it's very simple, but it's extremely powerful. So in NumPy, we're going to create these arrays, which look a lot like Python lists, but there are going to be significant differences. The first one is, of course, performance. If you go to the previous part when we were discussing the binary representation of numbers in Python and in NumPy, you're going to see the difference between them. So in this case, we're creating two arrays. And you will see, right, that the creation is extremely simple. The only thing that changes, we need to add this mp.array, and then we're passing, in this case, a list of numbers. This is something we will usually be reading from external sources. Now, how can you access individual elements of a NumPy array? This works in the same way as with a Python list. You can say, give me the first element, or give me the second element, and it's zero indexed, like, again, in a Python list. Slicing works in the same way. So in this case, up A0 to something, A1 up to 3, right? It's just getting a low level, right, and high level of the index. Negative indexing and steps, they all work in the same way as with a Python list. So if you know how to use a Python list, you will know how to use a NumPy array. There is one new thing right here, differently from a Python list, and it's what it's called multi-indexing. Let's say you have an array, in this case B, and you need to extract 3 elements out of it. You need the element at the first position, third position, and last position. You can just type B at 0, B at 2, B at -1. Or, and this also works for a list, or you can use, again, multi-indexing, which is from B, I want to select the elements in 0, 2, and -1. First element, third element, and last element, right? So you pass in another list containing the indices of the elements that you want to select. And in this case, the important part is that the result is another NumPy array. It's not just individual elements. You're creating another NumPy array, which, again, if you're processing, it's going to be a lot faster. So arrays have types associated, and this is related to what we were speaking before. As a NumPy array is continuously assigned in memory, the NumPy library needs to know what's the type of the object you are storing. You can't just store, anything, a string, a number within it, because it will not be able to provide the performance and optimizations for arrays that are not consistent in size. So for example, when we create this array that only had integers, by default, NumPy selected in64. This is because of the platform. It's a 64-bit platform. You can tune this and you can select, as we're going to see, other sizes in a second. When we created the array B that contain decimals or floats, it assigned a different type, which is float 64. Again, the default type is always, at least in this platform that is 64-bit, it's going to be float 64 and integer 64. You can always change that. You can say, actually, I want these, even though these are all integers, I want you to create them using a float type. Or, as we saw in our previous video, we can say it should be actually type integer 8, so the smaller integers for performance. For better performance, sorry. So moving forward, we were also going to see a few other types, like for example, strings and the regular objects. But as you're going to see, there is no point of storing these things in NumPy. NumPy stores numbers, dates, booleans, but not regular individual objects, as we're seeing right here. There is a way to store strings. It's perfectly valid, and it has its own type, and it's related to the Unicode representation, memory, etc. But again, NumPy is usually used for numeric processing. So the idea of NumPy is we can create multi-dimensional arrays. We can create what we had created before. This is a one-dimensional array, right? It's just one dimension. You can create matrices, which in this case are two-dimensional. We have 2 rows and 3 columns. And NumPy has a ton of attributes and functions to work with multi-dimensional arrays. So the first thing we're going to see is the shape of an array, which is 2 rows by 3 columns. How many dimensions it has? It has 1 vertical and 1 horizontal. We have 2 dimensions. And what's the total size of the array? In this case, the total size is 6, the total number of elements we have. Let's go 1 dimension further. Let's create a 3-dimensional object, a 3-dimensional array, which is basically a cube. In this case, for B, we have that the shape is 2 by 2 by 3, the number of dimensions is 3, and the size is the total count of elements, 12. You always have to be careful when you're creating these multi-dimensional arrays. If the dimensions don't match, like in this case right here, where we have this second list that only has 1 list in it, then the dimensions will not match, and it will just tell you, that the array is of type object, and the shape is only 2. It only has 2 elements. This is 1 element, and this is another element. So in this case, we've done it wrong, basically, and you have to be careful when creating these objects by hand. So how can you index and slice matrices? We've done it for a one-dimensional array. So we were selecting elements, individual elements, give me the first element, give me the second element, etc. How can we do it with a matrix? With a matrix, what we're going to do is going to be very similar to what we did before. The difference is that now we have to account for multiple dimensions. When I do give me A at 1, is it the column at 1 or is it the row at 1? Well, as you can see, it's the row. So this is going to be right here, 0, 1, 2, right? And there is also another dimension, right? So this is 0, 1, 2 in terms of index positions for our slicing. So here, how can you get the first element of the second row. In that case, you're going to first select the first row, the second row, and then select the first element, and that's what you get, number 4. But there is a better way, which is by using the multidimensional selection of NumPy. In this case, you're going to say, from this matrix, I want to select, and here you're going to pass in this case, you're going to pass dimension 1, dimension 2, dimension 3, dimension 4, etc. Right? And these are selectors for each one of those dimensions that you're passing. In this case, we say for row level, the element of position 1, the second element, and for column level, we want the first element in it. And it's the same thing as we did before. The advantage of this syntax, and keeping in mind and reminding it, is that it will also let you add slicing, right? So you'd say, I want to select everything from dimension 1, which is rows. So in this case, you say from 0 up to 2 is these 2 ones. The 2 is not included, upper limit, the same as Python. And then you can also pass other dimensions. So you say, I want to select every row. That's fine. But then I want to select from column level. I only want to select the elements up to 2. So these 2, and these 2, and these 2. Right? So 1, 2, 4, 5, 7, 8. These all works as intuitive as it gets. Remember, this syntax is the important that you need to keep in mind. Moving forward, for modification, you can say, I want to assign this new array to this entire row, right? So if the dimensions match, that's just going to work. Now, 10 is equals, it's added to the second row. Or you can just use what we call usually an expand operation, which is going to say, for row number 2, I want to assign the number 99. And NumPy is going to take care of expanding it into this corresponding array, given the number of dimensions that you have. So far, that selection, it's simple. We're going to see also is that NumPy has a huge advantage of containing a ton of operations you can perform on top of your arrays, your matrices, your multiple dimensional arrays in general. So the first one is all the sum statistic methods we have. So given an array, all these methods are already built in. The sum, the mean, the average, right? Standard deviation, variance, etc. And that also works for matrices. So in this case, we can get the sum, the mean, standard deviation, or we can do it per axis. So this is very useful. We can get here, let's compare these two. There you go. We can get the sum of these, what is this? First column, the second column, or the third column, and we can get it the first row, the second row, and the third row. So it's either this dimension 1, or it's a vertical dimension, which is axis equals 1, right? So per row, per column, or if you have more dimensions, you can just keep increasing the number of this axis, and that's just going to work as expected.
So I guess this is the first 2 columns here. So that should be this one.
Broadcasting of vectorized operations. This is a fundamental topic that we're going to talk about, and it's going to be extremely related to Boolean arrays. These are a few new things that you have to keep in mind when working with NumPy. And now we're going to talk about vectorized operations and broadcasting, which can be a counterintuitive topic at the beginning, but then you're going to understand how much sense it makes. It's one of the fundamental pieces of NumPy. We've seen how NumPy works in a very general way. We saw the multidimensional arrays and all those advantages, but you might be thinking, I don't need another library just to compute the sum or the mean. When I show you the vectorized operations, the broadcasting part, this is going to make a little bit more sense of why NumPy is so important. So to get started, we're going to have this array, which is A, right? That's just a very simple array. Vectorized operations are operations performed between both arrays and scalars, like in this case right here, which are extremely fast. They're optimized to be extremely fast. In this case, what we're going to do is we're going to sum the entire array plus 10. And what it means, we're going to see an example of what happens with that with Python. But what it means is that, let me show you the result, that each one of the elements within the array will be applied this operation. So usually that's the concept of vectorizing an operation. You have the number, and then this operation is applied to each one of the elements in here, or actually in this other one, right? So here, and here, and here, and here, to result in this new array. The operation is expressed at an array level, right? We say A plus 10, that's it. But then, again, internally, this is broadcasted to each one of the individual elements within the array. So in this case, we have A plus 10, we have A times 10, for example, which also, in this case, we're applying the times 10 operations to each one of the elements in the array, resulting in a new array with the result of that operation. And this resulting in a new array is very important, because as we're going to see, NumPy is an immutable first library. It will not, any operation you perform in an array will not modify it, but it will return a new array. If we check the status of A, we can see that the elements are the same. It has never changed. We are creating a new array and returning it. There are ways to override this behavior if you want, and all these operations we're performing in this way also have the interface of plus equals, minus equals, times equals, etc., which will indeed modify the array. So in this case, we're making a broadcasting operation, adding 100 to each one of the elements in this array, and now this operation was immutable. A was modified and it hasn't returned a new operation. If you remember from your pure Python skills, right, the correspondence of vectorized operations are list comprehensions, in which you're expressing an operation for each one of the elements in your collection, right? So that's a list comprehension. It's pretty similar to what we're doing with NumPy. The main difference is that this is all optimized and it's extremely fast. So the operations, or these vectorized operations, or this broadcasting, doesn't need to be only between arrays and scalars. It can only be between arrays and arrays. So in this case, we have A and we have B. I'm showing you right here. And we can do something like A plus B. And what you're saying is that there is a correspondence, right? So 0 plus 10, 1 plus 10, 2 plus 10, right? Let me do it in this way. 1, 10, 2, 10, and 3, 10. There you go. And that's the result we get right here. So for this to work, you of course need the arrays to be aligned and to have the same shape. But when that does work, then the operation is extremely fast in memory, and it's aligned. It's a vectorized operation as we've seen so far. Why is this topic of vectorized operations so important? Well, because of the following, which is Boolean arrays. And this is a very, very, very important thing. If you don't completely get it now, I ask you please to go and check the exercises we have for this lesson, because we're going to use it a ton. And we're gonna see that in Pandas, the same syntax, the same primitives of Boolean arrays apply, and we're going to use the same things. So why are Boolean arrays similar to vectorized operations? Well, all these operations we have performed here are just arithmetic operations, mathematical operations, plus something, times something, etc. If you look at the operators you have in your programming language, it's not only mathematical operators like plus or minus or times. You also have Boolean operators. And the question now is going to be what happens when you apply Boolean operations, when you apply Boolean operators to it. So given an array, what ways we had to select different numbers. For example, in this case, we need the first and last element. We do 0 and -1. That's the way we saw with NumPy. We also saw the traditional Python one, right? So we can say a at 0, and also we want to get a at -1. So this is the first way of selecting these elements we know. This is the second way with multi-index selection. And there's a third way, and this is new, which is with Boolean arrays, right here. So in this case, we're going to say, I want to select the elements in this order, right? And you're going to pass either true or false if you want to actually select the element or not, right? So if you have 4 elements, you have to pass 4 Boolean values saying, I want to select this element, I don't want to select this one element, I don't want to select this element, and I do want to select this element right here. So I want the first one and the last one, and the result will be the same, 0, 3, 0, 3, 0, 3. So far, it's nothing terribly new, right? So this is new, but it's not extremely complicated. We are showing you a brand new way of selecting data. You can select regular Python, multi-index, or a Boolean array. Now, you might be thinking, will I manually write true, false, false, true, true, false for, I don't know how many records you have, a million records? This is not scalable, right? You will not say to write all these true and falses. But this is actually very important because these arrays are the result of broadcasting Boolean operations. So we saw again a regular arithmetic operation like this, but we also have it for Boolean operations. So what happens if we ask a greater than or equals to the number 2, right? And array A is this right here, 0, 1, 2, 3. Then the result is false for 0, false for 1, because they're not greater or equal to 2, true for number 2, of course, and true for number 3. So all the individual elements that match this condition will have true and false in other cases. This is the power of Boolean arrays. We will be able now to combine these operations. So now we can do A greater than or equals to 2, right there. A equals A being greater than or equals to the number 2. The advantage of this is just filtering. We're filtering numeric arrays very quickly with a very familiar syntax, A greater than or equals to 2, and we just provide that as the index of the operation. It's pretty much what's happening right here. We're saying use this Boolean array, it's a Boolean list, right? It's a Python list with Booleans, to filter or to select elements based on that. But the question is, how do we construct that list of Booleans? Well, in this case, we have constructed it by including a predicate, by including a condition that needs to be matched. The result, again, is filtering. It's a query method. You're looking up some data. You're saying, give me all the elements that match this condition. So you can say, for example, these values can be, of course, calculated. You can say, give me all the elements that are greater than the mean. Or you can actually provide other Boolean operators, like, for example, all the elements that are not greater than the mean. So that means they're less or equals than the mean. Or you can also include other Boolean operators like or and. So or and in NumPy are expressed with a pipe or an ampersand, because we can't use just the regular or and in Python. We can, but it's a good choice. They've selected this. So again, this is the concept of Boolean arrays. We are going to construct these arrays that are just Boolean representations or Booleans based on conditions, right? So we have this matrix, and we're going to say, I want to select this one and this one and this one, etc. So in that case, this is the result right here. This is the result of that, and we can generate a dynamic Boolean array. We never manually type all these, right? We don't sit and say true, false, false, true, etc. We just run a query, a filtering option, a Boolean operation, which results in a Boolean array, and now we can use it as filtering. So again, the idea here is that the operations we saw in broadcasting before, a times n, are also defined for Boolean operators. Boolean operators return Boolean arrays, which can be used in filtering. That's the idea of all of it. And you can even combine these operations. You can say a equals 0 or a equals 1, a less or equals than 2, and it's also divisible by 0. You can combine all these queries. So now it looks a lot more powerful than when we were doing before. So moving forward, talking about linear algebra very quickly, and we're approaching the end of the NumPy lesson. The important part of linear algebra is that NumPy already contains all the most important operations for it, already optimized with low-level semantics. So it's going to be extremely fast. Dot products, cross products, and all that, transposing matrices, all that works as expected. And again, this might be very important, especially for example, machine learning, etc. It's extremely important. And finally, to wrap up what we saw in our binary explanation at the beginning, what you might have skipped, is the difference in sizes between NumPy and Python, the differences in terms of performance between them. So in Python, a regular number, this is just a regular integer in Python, the total size is 28 bytes. In order, and then just let this think for a second, the total number of bytes, not bits, bytes, that you need in Python to store a simple number as the number 1 is 28. You need 28 bytes to store just the number 1. It's extremely space consuming, right? It's not very efficient. Larger numbers will even take more bytes to store them. What's the size of the integers? Well, we've seen it. We have, for example, we can create integers with 8 bytes. We can create integers with 1 byte, right? Which were something like, here we have np.int 8. We already know how many bytes has only 1 byte, right? But you can have control of how many bytes or bits, right, your numbers will take. And you can see here the difference between the size of an integer in Python, which is extremely large, 28 bytes, and NumPy. And also the difference in performance. Let's say, for example, we want, here you have also the difference in size of lists, which is also significant, but I want to focus in performance. We have two elements. We have one list that has the first 1,000 numbers, and we have a NumPy array that has the first 1,000 numbers. And we're going to perform the same operation in both of them. Let's use the Python one first. We're going to do the Python one first. In this case, we're squaring all the elements in the list. Okay, the elements is squared, and then we're summing all the operations. Right, so we express it as saying create a new list squared for x in L, and then sum everything. How much time it takes? 321 microseconds. We're going to do the same thing with NumPy. We're going to say np.sum a squared. And you're going to see that it's a lot faster in the NumPy perspective than the Python perspective. And these are all very, very tiny operations with small numbers. What happens if we add more numbers? Let's add 2 more numbers here. Let's add 2 more numbers here, and we're going to do the same 2 operations. So you see here, the units have even changed. We're still in the microsecond layer here with NumPy, and we've gone to the millisecond layer in Python. So as the size of your objects increase, NumPy will prove to be extremely fast compared to Python. So there are a few other functions you can see here, for example, extracting normal random numbers, etc. I'm going to let these for you to look if you are interested in them. And remember, you have the exercises, which can help you solidify all the concepts we've discussed. And we're going to move forward now to work with Pandas. We're going to see also visualizations. We're going to keep moving forward this data analysis with Python tutorial. Python, which is extremely large, 28 bytes, and NumPy. And also the difference in performance. Let's say, for example, we want, here you have also the difference in size of lists, which is also significant, but I want to focus in performance. We have two elements. We have one list that has the first 1,000 numbers, and we have a NumPy array that has the first 1,000 numbers. And we're going to perform the same operation in both of them. Let's use the Python one first. We're going to do the Python one first. In this case, we're squaring all the elements in the list. Okay, the elements is squared, and then we're summing all the operations. Right, so we express it as saying create a new list squared for x in L, and then sum everything. How much time it takes? 321 microseconds. We're going to do the same thing with NumPy. We're going to say np.sum a squared. And you're going to see that it's a lot faster in the NumPy perspective than the Python perspective. And these are all very, very tiny operations with small numbers. What happens if we add more numbers? Let's add 2 more numbers here. Let's add 2 more numbers here, and we're going to do the same 2 operations. So you see here, the units have even changed. We're still in the microsecond layer here with NumPy. We've gone to the millisecond layer in Python. So as the size of your objects increase, NumPy will prove to be extremely fast compared to Python. So there are a few other functions you can see here, for example, extracting normal random numbers, etc. I'm going to let these for you to look if you are interested in them. And remember, you have the exercises, which can help you solidify all the concepts we discussed. And we're going to move forward now to work with Pandas. We're going to see also visualizations. We're going to keep moving forward this data analysis with Python tutorial. And now it's finally time to talk about Pandas. It's the most important library that we use for data analysis in our day-to-day basis with Python. It's a library that will aid in the entire process of your data analysis project. You're going to start getting the data. Step 1, getting the data from multiple sources like databases, Excel files, CSV files, etc. That's all going to get into Pandas. You're going to be processing the data, right? So you're going to be combining, merging, doing different types of analysis. You're going to be visualizing the data, right? So a bar chart. You're going to be visualizing the data with Pandas, and you're going to be creating reports. You're going to be also doing simple statistical analysis. You're going to be doing machine learning close to it with the help of other libraries, but everything from the platform that provides the Pandas library. It's, again, one of the most important libraries in the data analysis, data science ecosystem with Python. Pandas has recently released the version 1.0, so we are talking about a very mature library. It's been around for a long time now, and again, it's the primary library we use in Python for data analysis and data science. So I'm going to do a quick introduction to the data structures that Pandas has, and we're going to understand how they work, so you can start building, right? We're going to start building the foundations. I need you to be very familiar with the way the data structures from Pandas are processed, and then we're going to move into other things like reading files, grouping data, etc. So to get things started, we're going to talk about the first data structure that Pandas has, which is the series. In reality, Pandas has 2 main data structures that it uses all the time, and it's the series and the data frame. The data frame is the one you will probably be more familiar with. It looks just like an Excel table. But we're going to start first with a series. Okay, so just stay with me here. We're going to talk about a series for a second. In this case, we have imported Pandas, and we have also imported NumPy. As you might imagine, as I told you before in the NumPy part of this tutorial, we were saying NumPy is fundamental for data analysis because every other library, Pandas, Matplotlib, they all sit on top of NumPy. And you can see it right here. We're going to be using some features from NumPy within this lesson too. So this is a series in Pandas. What you see right here, it's the concept of a series is this ordered sequence of elements, right? All indexed, right? They are all indexed by a given index, of course. And you might think that this looks a lot like a Python list, right? So in this case, we're storing the population of countries, right, in millions of inhabitants. In this case, it's G7pop is because we're getting the population of the group of 7. You can consult the Wikipedia page. But basically, we are storing population in here in this series. And again, it looks a lot like a list, but we're going to find a ton of differences in here. So the first one is that the series has an associated data type. And this is something we saw in NumPy. When a NumPy array couldn't hold different type of objects, we were only having one type of object. In this case, it's float 64. So all the numbers of this series will be of type float 64. before, the underlying data structure that Pandas is using to store these objects is a NumPy array. So a second difference we see very quickly is that a series can have a name, right? So now when we display the series, we see that it has a name. Now it might not make a ton of sense, but once this series is part of a data frame in the form of a column, then the name is going to make a lot more sense. So moving forward, again, we saw that it has a type, and again, this is because the data is backed by a NumPy array. You can always consult. You can check values of a series, and you're going to get the array that it's backing up that Pandas series, right? So you can see that it's a NumPy array. Once you have these series, we were just consulting here, G7 pop, you can select elements as you would in a regular list, right? So for example, give me the first element, give me the second element, the last element, etc. And that's because a series inherently has an index, similar to a list. A list, when you create a list in Python, right? So if I create L equals A, B, and C, there you go. There's something wrong here, missing a quote. This list, we don't say it, right? But the idea is that there's an index here. There's 0, this is 1, and this is 2, right? In the Pandas series, this is a lot more explicit. Each element has an associated value within it. And you might think that it's pretty much the same thing. They're both the list and the series. They're both sequences. They're ordered sequences of elements. But we're going to see that there is a fundamental difference, and is that we can arbitrarily change the index of a series. So by default, when we created it, we didn't assign any indices. So by default, it was a range index from 0 up to n-1 elements. But you can actually arbitrarily again say what is the index of your series. And in this case, this data structure, this series has now these indices that we're saying right here. Why is this important? Because now we're going to be referring to these values not by a sequential position, but by a name, by a label, by the index which has a meaningful name for us as humans. Okay. So now this thing looks a little bit more like a dictionary, we could say, than a list. We started thinking that a series was similar to a list, but now we can think that a series is similar to a dictionary. But wait, don't get me wrong here. The series has a fundamental trait, and it's that it's still ordered. Something that didn't happen with dictionaries. Dictionaries in Python are not ordered. Actually, in Python 3.7 they're ordered, but we shouldn't be thinking that they are ordered. They're unordered data structures. In this case, a series is indeed ordered. So it has both those advantages. It's ordered. Canon is always before friends. That's as we decided to create it, but also it has names or labels or keys associated with the values as a dictionary. So this is creating the series from scratch, right? All these methods, you can see you can create a series by passing the index. It doesn't have to be a two-step process where you first create the series and then add the index. In this case, you can do everything at once. And the indexing is now going to be done by those indices, right? So those labels that make up the index will be used to index specific data. So G7 pop, we see, has these countries with these population. And now, before the index, we were saying, I want to get what's the population of Canada. And then we had to remember, what was the position of Canada? Oh, it's the first country. So we have to do G7 pop 0. With the index, now we can just insult. What's the population of Canada? What's the population of Japan? And as you can see, the syntax is the same as with the Python dictionary. Just pretty much the same. You pass the key and it's going to get the value. So again, summary. The advantage of a series is it's a ordered sequence of elements backed by a NumPy array, very efficient, very fast. But it also has an index that can take any labels that we pass. So it's going to make it a lot better for indexing. You can still, when you have a series, you can still get the elements by the sequential ordering. After all, it's a sequential data structure. It doesn't matter if you have an index. You can still say, hey, I know we have an index, but I still want to get the last element, or the first element, or the second element. And you're going to do that by using the attribute iLock. Okay, so you can say to this series, from this series, I'm going to iLock, locate by sequential position, this element, the element in position 0, or the last element. And that still works as expected. Series also support multi-indices, as we saw with NumPy. So in this case, we can get 2 elements out of 2, 3, n, any elements. You can pass multiple indices. And the same thing happens with sequential multi-index. Series also support range or selection or slices, but there is a fundamental difference here. This is very important, pay attention. There's a fundamental difference with Python, and it's that in Python, the upper limit of a slice is not returned. So from our list that we created before, if I do L up to number 2, I don't get the index C, right? So this is 0, this is 1, this is 2. 2 is not included. In a Pandas series, the upper limit is indeed included. So when you ask from Canada up to Italy, Italy is in the result. Okay, so this is something to consider when using index selection in Pandas. I think this is still valid. I understand the reasoning behind it. It's just different from Python, so you should remember. Boolean Arrays, which was a topic we discussed in our previous lesson of NumPy. Boolean Arrays is still a thing in Pandas. The difference is we, instead of saying Boolean Arrays, we should say Boolean Series, right? The idea is that we will be able to perform operations on top of series. So for example, right here we have mathematical operations on top of series. In this case, we have the G7 pop, which, as I told you at the beginning, is in million of inhabitants. If we want to get the series in just units, we will need to do G7 pop times 1 million. And there we go, now it's in terms of units. These operations, right, these vectorized operations, these broadcasting operations, can also be performed with Boolean operands. So instead of a multiplication, a summation, a subtraction, etc., we can use a Boolean operator. So in this case, we can ask, what are the countries that have more than 70 million inhabitants? We will receive the result is a Boolean array. It's not a Boolean array, it's a Boolean series, you know it. But basically, it's the same concept as with a NumPy Boolean array. Canada, France, they do not have more than 70 million inhabitants. In Germany does have more than 70 million inhabitants, here 80, and the same for Japan. So Japan here is the same, and the same for the US. The US also has more than 70 million inhabitants. So again, the Boolean array or Boolean series in this case works in the same way as with NumPy. And selection also applies. So I can now select, I can say, give me from these series, G7 pop, all the countries that have more than 70 million inhabitants. The value is more than 70. So now, again, we are building filtering. We're building a query language, if you want, on top of Pandas. We're selecting data based on this condition. Remember, if you ever have trouble remembering all this, the idea is that you can always track down the way this index is being built. In this case, it's not that this selection knows anything, this first selection knows anything about how to select countries with more than 70. This operation was performed first, which resulted in this series, and now this series will be indexed by this array, this Boolean array. And the result is as you can see it. And again, these operations can be run with calculated methods and all the operators we saw in our previous lesson, which was not, which was or, and this regular type, or, and, ampersand, which is the and. All these can be applied in any order you want. So if we read this thing, which is complicated on purpose, we're saying, give me all the elements that are above the mean minus 2 standard deviations, or below the mean, actually above the mean, and here was below the mean, or this is incorrect, but it doesn't matter. It's just an or operation between two ends of the, it's above the mean minus the standard deviation. So we are applying this operation or, right, that operation we had before. So the not, the or, and the and, they all work with Boolean selection as well. The operations we saw from a mathematical perspective, in statistical operations we saw in Numpy, some mean, average, standard deviation, we were actually using standard deviation before. They're all still relevant in this case, but also you can use traditional Numpy functions with a Pandas series, because again, a Pandas series is internally backed by Numpy Array. So this is all the same, as you can see. Here's an example that it's a little bit more clear. We're getting all the countries that have more than 80 million inhabitants, and all the countries that have less than 200 million inhabitants. So it has to be above 80, but it also has to be below 200, okay? Or in this case, we say either above 80 or below 40, or below 40, right? So that's with the or operator or the not operator. Modifying series is relatively simple. Whenever you have a value, you can just assign it altogether. In this case, we're saying Canada is now 40.5. I don't know why, we just wanted to do it. This is by index. You can also do it by sequential position. So in this case, we're going to say the last country should have 500 now. So we're going to see right here, the last country has 500 now. Or you can also modify elements based on a Boolean selection. So you can say all the countries that have less than 70 million inhabitants, all these from our previous query, all these will now be 99.9. So as you can see, it has changed all these countries. So the assignment works by direct indexing or also works by Boolean indexing. And this is going to be extremely important when we are cleaning data. So let's move forward and start talking about data frames. Now before, you have exercises for series and also for data frames, so I recommend you to check them out. So talking about data frames, this is what a data frame is going to look like. It's pretty much the same thing as an Excel table. So this was our series, and this is going to be our data frame. It's a table, so it looks a lot like an Excel spreadsheet, and actually it's very common to create Pandas data frames out of CSV files, which are tables, basically. And I'm going to create it. We created with these data frame objects. And I created, there you go, this is our data frame. And as you can see, right, it has columns that we have assigned. In this case, we were designing the columns, and we have rows of values right below each one of these columns. What's the similarity with series? And it's that a data frame column will be basically a series. So we can think a data frame as a combination of multiple series, one per column. We're going to assign an index to the data frame the same way that we did with series. So in this case, this is our data frame. Sorry, right here, this is our data frame. Then it has the index, right, and it has the columns as we had before. What columns do we have? What's the index of the data frame? These are all attributes that you can consult. There are a couple of very interesting methods from data frames that we use all the time. The first one is the info method. That's going to give you quick information about the structure of your data frame. Right? So it's going to tell you what columns you have: population, GDP, surface area, HDI, continent, and it's also going to tell you the types and how many null values you have. It's actually telling you how many non-null values you have, but we use this when we're cleaning data to quickly identify those columns that have missing values. We can check for the size of the data frame. We can check for the shape, and this is similar to a matrix, right? A two-dimensional array in Numpy is pretty much a data frame. And also similar to info, it was again to check a summary of the structure of the data frame. We can also use this which is going to give you a summary of the statistics of the data frame. And in this case, what we see is that for each numeric column, only those columns are numeric. Continent is not here, for example. This is continent, so you can see the type is object, is a string, basically. All the numeric columns, we're going to have summary statistics for them. So for example, for population, how many elements we have? What's the mean, right? What's the average value? What's the standard deviation, the minimum, the maximum, and in between a couple of percentiles, 25th, 50th, and 75th percentiles. So this is quick summary statistics, and we do this a lot. So keep in mind, this dry method is very popular. As you could see in the info method, the columns have associated types. Okay, so this is very important. The continent is an object. That means that it's basically a string. HDI is a float, and surface area is an integer. And that's because Pandas is automatically, through Numpy, is automatically recognizing the correct type to assign to each one of the columns. This is similar to what we saw with series, in which the series contain an actual data type. A series was part of a given data type, so that's something you cannot change. And in this case, checking value counts, you can have a quick reference of the types of your series. So moving forward, how will we will be selecting data from series? Well, there are a couple of methods. And this might be a little bit confusing. So what I'm going to do is I'm going to skip and just going to give you a quick reference first. And then you can read, if you want, through the process we follow here. Given a data frame, and this is just two quick rules. Given a data frame, you're going to select by index using the lock attributes. So the lock attribute will let you select individual rows. So for example, we want to get Canada. Canada. That's the value of Canada. The iLock attribute will let you select, similar to the series, the row by sequential position. So let's say we want to select the last row. In this case, it's the United States of America. So again, look, let you select rows by index. Give me the row under this index. iLook will let you select rows by sequential position. Give me the last row, the first row, the second row, etc. And finally, without using look, without using iLook, just by saying df at something, you are selecting that column. Give me the entire column population right here, the entire column population. So what you're saying here, first of all, this is a quick reference. .lock will give you an element by index. iLock will give you an element by position, a row by position. And just doing df at something is going to give you the element, the column, sorry, that you are passing. So it's like both look and iLock work in a horizontal manner. Give me this, while df at whatever works in a vertical manner. It's just getting you a given row. But something more interesting here is that all the results, this one and this one and this one, they're all series. What are being returned are series. So that's what we saw before. And the way it works is, first, if we focus on this last example, we're going to see that it's pretty standard. Just this series right here is the one returned. And remember, it has a type and everything, so that's fine. If we ask for a row, like in this case, we can get, for example, here, Italy. There you go. The result is also a series. But what you can see here is that this thing is kind of transposed in a way that here was the values of the series. Population is here, and GDP is here, and surface area is here, HDI, and continent. And here you have the values. So it's being transposed, right, from vertical to horizontal in a regular series manner. And the index of the series is extracted as the name that the column had. So in this case, the name right there is the value of the index that it had. So you can read more about it right here, but I just want you to remember these rules. .lock you select by index, .ilock you select by sequential position, df at something you go by column. There are times when these might not apply, or not might apply. There will be some issues. So for example, if your index is numeric, you might have issues with this form or that form. Just respecting these three for now, it's going to get you any element you want to get either by row or column. So from what we've seen, all the slicing also works as expected. So we can get, for example, Italy, or we can get France up to Italy. So the upper limit is included. But again, it's .lock, and we select it by indices from France to Italy. We can also do the second dimension, similar to the way we worked with NumPy. We can do second dimension here, and we can get all the countries are from France up to Italy, including Italy, but only the population column, or population and GDP. So here you can see this second dimension being applied, the concept of multiple dimensions in selection being applied also to Pandas. For iLook, it works in the same way the multi-index and the slicing. So we get, for example, from 1 to 3, right, in sequential positions. In this case, the upper limit is not included. So that's another difference from what we have. And we can also do multi-dimensions. We can say, give me the countries from 1 to 3, and the column should be 0, 1, 2, 3. Should be the fourth column, the column under index 3, which is HDI. So that also works as expected. And again, recommended, always use iLock to select rows, and just use the naked data frame to select columns, as we saw before.
Be right back. I have no idea which one it is. I think it's one of this show. I'm not sure. No, it's probably this one. 13.11.9.7. I think it's this one.
Now, moving forward, conditional selection, Boolean arrays, Boolean series, whatever you want to call it. This also works for data frames, and it's very important. It's a way to filter data. It's a way for us to consult data when we need it. So in this case, what we have is we want to select all those countries which the population is greater than 70. Okay, so all the countries that have more than 70 million inhabitants, similar to what we did with the series, but in this case we want to do it with the data frame. So what you're going to see here is that we're going to construct a Boolean series as we did in our previous video, right? So every country with more than 70, false, false, true, false, and we're going to inject that result, that Boolean series, in a .log selection. Give me all the countries which match here the true value in it. And remember, just this is kind of a mnemonic or a way to remember, the way Pandas knows how to filter things is by matching this index, right, from the resulting series with this index of the resulting data frame. These are two different objects. They're completely different objects, but their index match. So here, Japan match, Germany match. So here, Germany and Japan, they are the same, and that's why that thing is working as expected. This is just the first dimension, which is give me these rows. You can also add a second dimension saying, give me these columns, or these columns, right? So that still works as desired. So what about dropping stuff? You can say, whenever you have a data frame, you can say, give me just these pieces, or you can say, drop the others, right? It's just pretty much the same. Dropping is very simple. You can drop by index, drop this value, drop Canada altogether, period. Or drop these indices, Canada and Japan. Or you can also drop columns, drop population and HDI as columns. These ways also have a more advanced usage, which is with the axis, similar to NumPy. I don't recommend them so much, but you can still use them and see them in here. So all the operations we've seen so far, they're all working. The most important part here is the broadcasting operation that we're going to do between series. So we're going to create a new series, crisis, and I'm going to show you what it looks like. So we have here crisis, and we're going to perform a broadcasting operation between these. I'm going to show you what this thing looks like first. Between that, so these data frame, and the crisis. And the result will be that we will subtract, I don't know what's this number, 1 million, subtract 1 million for each value in here, and we're going to subtract 0.3 HDI for each one of those. So what you can see here is, again, this alignment between columns and indices. The GDP here is matched with this GDP, and the HDI is matched with this HDI. So there are two different objects, two independent objects, this series and this data frame here. But when we combine them with an operation like this, the columns in this case are aligned, GDP and HDI, and they work together. So you're going to subtract this value in all these columns. Let me remove this. You're going to subtract this value in all this column for all these values. You're going to subtract this value here in this column for all these values. That's the way it's going to work. So moving forward, what about modifying data frames? I want to show you something, and it's when we were dropping stuff before. We were not actually modifying the data frame. So here we did df.drop Canada, but df still has Canada in it. And that's because, similar to what happened with NumPy, these operations are all immutable. They are not changing the underlying data frame. We're creating new data frames that store the result of the given operation. So in this case, df.drop Canada, the result is that this new data frame, but the underlying data frame is not changed. That's because, again, they are immutable operations. 99.9 operations in Pandas are immutable. There are ways to change it. There are ways to make the changes permanent. But for now, I want you just to think that everything is immutable. Whenever you want to perform an operation, it's going to create a new series. If you wanted to keep track of this, you will just need to do something like df2 equals that, or even df equals, just to modify the current data frame. Again, there will be a way to not do that, but we're going to say it in a second. So modifying series more explicitly, modifying data frames more explicitly. How can you create a new column? Well, very simple. Assign the column as it is. Say in this column right here, it's similar to say here language. Oh, it's just read only. But if I say language equals, and I can just write whatever I want. In this case, what we've done is that the language, let me show you what language had. In this case, was a tiny series. It didn't have elements for all the indices in the data frames, but that doesn't matter. Pandas will match all the indices that actually exist, and it will leave blank the rest. This NaN is what we use for a blank. It's not a number from NumPy. We're going to talk more about it when we start doing cleaning data cleaning, sorry. So again, length, France, Germany, Italy, you can see the values are all up there. What happens if you want to change a value? The language series already exists. You want to change it, or column already exists. You want to change it. So in this case, we're going to say df language equals English. So we're going to change it all together. And df now will be affected, and all the values of language will be English. How can you realize when there is an operation that is changing the underlying data frame, the underlying series, or the underlying NumPy array? It's usually when you have an equal symbol. Remember NumPy, we saw something like plus equals. In this case, whenever you have an equals symbol, you are modifying the underlying data frame. So for example, check this out. The rename function or method of a data frame will let you pass columns and indices to rename. So in this case, we want to change the United States to USA, the United Kingdom to UK, and Argentina to AR. Argentina doesn't exist in this data frame, but that doesn't cause a problem. That's what we want to show you. The US and UK were modified correctly, and HDI was modified correctly, and APC, which doesn't exist, didn't cause any problems. Now, why am I showing you this? Because remember, these operations are immutable. If I check what's the state of the data frame, we see that the original data frame has not been changed. HDI is still HDI. It doesn't matter if we renamed it before. It's still the same data frame. The same thing for these indices. All these operations are immutable.
So I guess this just creates a new column here, a new row with longest streak assigned to these numbers. Creates index equals to name, then longest streak. At the bottom here. Probably gonna have to look at this again later, probably. Because I think I understand it, but not very.
A few more examples of modifying data, just for you to look at. And something that is very common for us is creating columns that are combinations of other columns. So again, this is read-only, but you can imagine that I could do here something like, for example, GDP per capita, right? If I go here and I do GDP per capita, and here I say is equals to the GDP, this column, divided by this column, right? So I do something like B3, actually C3 divided by B3, right? And then we would extend the values all the way along here. In Pandas, we do something very similar. We can do just any column, we can just perform operations, broadcasting operations between them. In this case, it's GDP by population. And we can assign that series, which is a result, right? The result is a series. We are going to assign that series to a new column. So GDP per capita, there you go, is now a column of our data frame. Again, all these broadcasting operations are extremely fast. They're backed by their Numpy array, and they result in a series. So very quick statistical information, a few methods, right, to do summary statistics. We saw them with the describe method, but minimum, maximums, mean, median, all that works as expected. Something that I want you to note here, if possible, is that with Pandas, we have, I'm going to change colors here. We're going to use red. With Pandas, you have this concept of a data frame, right? Data frame that has multiple columns and multiple rows. And these operations are resulting in just one series. So in Pandas, you have your data frame, and you have your series, and we could say we have individual numbers. And it's like always, the data frame is always resorting back to this. It's like some operations will just return a series, and the series can be used in a data frame, right? So in this case, these resulted in a series. But then we immediately use the series to set the value of a column, right? So that's why understanding series is so important. So there are a few more assignment exercises for you here, so you can check them out and complete them if it's going to make a little bit more sense once you're working with it. Finally, I want to give you a very quick introduction to reading the external data and plotting. And to do that, we're going to use a few methods that are very popular in maybe we can look them up very quickly here. We can say read CSV. We're going to use the read CSV function from Pandas. So this function, read CSV, and as we have read CSV, we actually have a few others. Read SQL, read Excel, read XML, read JSON, there are multiple ones. Read HTML, we will be able to automatically parse an HTML page and read it. So a few functions like these, like what we're going to do with these read CSV, right? Here's the structure of it. A few of these functions will let us import data from an external source into our Pandas workflow. So in this case, what we're going to read is this BTC market price value. So it's right here. If I open the CSV, this is what it looks like. It's the date of the price taken, read, and the value, the timestamp and the value, the timestamp of the value. Note aside, the price of Bitcoin in 2017, now it's close to $9,000, I think, but just a note on the side. But again, this is a CSV, and this is a CSV that we're going to be reading. To do that, again, we're going to use this method, read CSV. The method will automatically parse the CSV as expected, and there you go. And the process now will be for us to start tuning it to to get to the right point. So I'm going to show you a few customizations we can do with the readCSV function. So the first one, and sorry, let me tell you first, we have a ton of attributes here. So we have a ton of customization to do with readCSV. You will not remember all this. You will not remember everything out of the top of your head. So don't worry, you can always go back again to the documentation and just practice. It's going to come naturally. So the first thing, the first row of the CSV was considered to be the column names. So in this case, this file doesn't have a column name. Let's say I add it. I'm going to do timestamp price. I'm going to save it. I'm going to reread the file. I'm going to reread it. There you go. So by default, Pandas is assuming that the first line of the CSV are the columns. I'm going to go back into what it was, right? I'm going to show you. Again, that's the assumption that Pandas is doing. We can, of course, change that assumption because in this case, our CSV file does not have column names. So we're going to just say header equals none. And this is when we start seeing the attributes that we're going to use from the readCSV function. readCSV, and we're going to do header equals none. For us, it's going to be none. That means don't read a header. Don't try to infer a header from the CSV file. And the columns are 0 and 1. So now I'm going to change the columns and I'm going to say, actually, it should be timestamp and price. And now what I'm going to do is show you the first rows. So you're saying here that I have this df.head method that I'm doing. That's because this is a significantly large file. So we're going to say, not that long, but at least it doesn't fit in my screen. What's the shape of the CSV or the data frame? It has 365 rows and we have 2 columns. So we can do df.info, for example, to have a little bit more reference about it. We have 365 values. There are no null values, and price is actually a float. The timestamp is an object, and we're going to fix that in a second. And sorry, the df.head and df.tail are the methods we use to get either the first n files, or the n rows, sorry, or the last n rows, which are 5 rows. By default, you can change that and say, show me the last 3 rows, for example. That's something you can do. And again, the types. So the types is the timestamp, in this case, the timestamp column was not properly parsed as a date. It was parsed as an object, as a string, which we don't want. So we're going to use the function pd.toDaytime, something we're going to explore in more detail in the data cleaning course, of the tutorial. We're going to use the toDaytime function to turn this column df.timestamp into an actual date. And now we're going to say df.timestamp equals to this function resulting. And now everything looks as expected. There is one more change that we want to do, and we want to set the index of the data frame to be the timestamp. Because by doing so, we can quickly access price information. Let me see, what was the price of Bitcoin in 2017, 09/29. And I make a mistake here. I forgot the LOC. There you go. So we have the value of Bitcoin on this particular date. Forgot lock. Remember that to get value from a particular row, you have to do .lock. There you go. So we are getting that particular value because we've made timestamp the index. We can access the value directly from the index. So what happens if we want to turn this thing into an automated script, for example? We want to run this process every day at 5 a.m., whatever. We want to read the CSV, strip the columns, rename them, turn them into timestamps, etc. This is what we've done so far. Read the CSV without a header, create the columns, turn it into a datetime, timestamp into a datetime, and assign it to the index. And that's the result again. Well, actually, the readCSV method is so powerful that it will let us do all these actions in just one call of the readCSV method. There are parameters that will let you customize the behavior to achieve the same results that we did with 4 lines of code right here. So in this case, we're going to say, read the CSV, don't assign a header, that's something we saw already, or don't infer a header from the first line. These are the column names, so we don't need an extra line. We can just say, these are the columns names. Oh, and by the way, the first column is going to be the index of the data frame. Oh, and also, parse the date, the index, it's a date, so parse the date, and we have the same result as before. So now, I'm going to try the same thing. There you go. As you can see, it's working. So very quickly, Pandas plotting. All right. So what we're going to be doing here is I'm going to show you very quickly. I don't know what's this thing has a vertical scrolling. I want to show you very quickly that you can create plots with Pandas in just a breeze. It's so simple to create plots. So in this case, what we're going to be doing is, given a data frame, you can always invoke the plot method. And the plot method, what it's doing, it's using the matplotlib library, something that you can check if you want in the docs. But for now, it's not necessary. With this, we're going to be more than enough. What it's doing is just using, again, the regular plot library, as you can see, the matplotlib library, which is part of the standard PyData stack. And again, for us to access using Pandas, it's extremely simple. Just df.plot, and you're done. You can set the plot as you want. We're going to see more details of matplotlib, so don't worry too much about that later. So there is a more challenging example here that I can just run very quickly. You can inspect the process we follow to fix the data, but this is what we have. There you go. And what you can see right here is the difference between the Bitcoin and Ether in this period of time right here, and they are both plotted in the same chart. And that's because this is the resulting data frame. We have Bitcoin on one side and we have Ether on the other side, and we are plotting it right here. We're creating one plot with all of it. And we are noticing this empty value right here. So what we can do is we can go from December the 1st up to January the 1st, this period. So we can select that period using .log, and we can just go ahead and plot it again. And this is what you see right here, the gap that we're seeing. So again, this was the introduction to Pandas. We have a real life example of Pandas following up. Also, we have a little bit of more data cleaning and reading other interesting files and sources of data for getting more data into the pipeline, right? So the idea is going to be showing you how you can import data from Excel, from SQL, and then do the actual processing and analysis. Now it's time to talk about data cleaning. We have arrived to that point in our tutorial in which we have pulled the data. I've shown you how to manipulate it with Pandas, the beginning, at least the introduction to data manipulation with Pandas, and now it's time to properly fix it. For the sake of brevity, we are skipping a few parts of the process of data cleaning, especially you're going to find in this first notebook that we talked about basics, conceptual, mixing data with Python, with Numpy, and we're going to miss a few other things, but I'm just going to mention them in a pretty general form, and then you can, of course, dig deeper. You can check out our courses if you want to know more about it. Usually when we talk about data cleaning, where it's from a more conceptual level, we're going to talk about a 4-step process. The first step is usually finding missing data, which is the simplest problem to identify from a data set when something is missing. So you have car sales data and there is a car that has no name, right? Or there is a car that has no price, right? So there is a number missing, or there's a category missing, or there's a string missing. And of course, each one of those is going to have a different meaning. How to fix a data set that is missing data? It can be very simple if you can just, for example, drop the record. If you can fill the value, right? So for example, the price is missing, you can fill it with the average value of the sales data or something like that. Or it can be very complicated if the value is important, if you can't move forward until you actually find that missing value. And it can involve something like picking up the phone, calling your ETL team, asking what's going on, that the data is missing, or even if you're buying the data, you have to call the vendor, ask them why if you're paying for that and there's data missing, etc. So it can be a very political process. It depends what's your use case. But again, from a technical perspective, identifying missing data and fixing it is going to be extremely simple. Once you have fixed the missing values, then you start looking for the data is, and assuming the data is not clean yet in this process of data cleaning, the second step is when there are invalid values. So you have, for example, a column that is price and there is a string within it, right? So you're expecting only numbers and there are strings in it. So then it's not going to be that complicated to identify. It's not going to be that complicated to fix it. But again, we're increasing the complexity until at the end of this data cleaning process, we're going to reach problems that have to do with the domain of the data you're looking, right? So for example, you have a column that is customer age and there is a value that is 170, right? So that is not an invalid value. It's a perfectly valid integer. The problem is that given the domain, right, we're speaking about customer age, is highly unlikely that a customer is 170 years old, right? So in that case, the value is completely valid. There is no missing data. There is no invalid values, etc. It's just about the domain. And this is when things get very complicated, because in this case, the example of age is something that resonates with all of us. We know about age of humans. But if you're working in a domain, if you're working as a data analyst in a domain that you don't know much about, right, then you might not be able to judge if a value is invalid or not. If I am working in a biology lab and I have something like white cells count per milliliter of blood, I don't know what's a good value or what's an invalid value, right? So it's something you need to know the domain. So that's usually the most complicated part of data cleaning. When you reach the limit of everything is valid, everything checks out, and now I need to make sure that this value is valid for this domain that we're working. So again, this is the spectrum that we're going to be revisiting today. So to get things started, the way Pandas works with null values is it has 4 functions, which actually there are synonyms. So it's going to be relatively simple. Just trust me on that. There are a few things first. Everything that Pandas does in the process of missing values is related to the way NumPy works. So again, we're skipping it. You can go to that notebook, check it out by yourself, but it's extremely simple. NumPy has this object, nan, not a number, to identify a missing value or a null value. In Python, we also have the none value, but again, in Pandas and NumPy, we're going to use nan, none. And there are, in this case, at the beginning, we have these 2 functions, isNull and isNA, which are complete synonyms. We're going to find also isNull and, I don't know if we have it, isNA, and they're also complete synonyms. So null and NA for Pandas is the same. You can use the one you prefer. Sadly, I like isNA because it's the way I learned it. I think for my students, I usually recommend isNull because it feels more correct and it feels more self-explanatory. So you can use the one you prefer. If you can use isNull, I think it's going to be better. If you get used to isNA, then you're going to be on my side. Just do whatever you prefer. So again, isNull is going to say true or false depending if the value is null or none, right? And of course, not null is going to be, or not NA is going to be the opposite. So not NA of not a number is false and not NA of 3 is true. If you get to this first notebook, you're going to see all the falsy values on the truthy values. In terms of Python, anything that is not empty or none, etc., is going to be considered to be truthy. So anything you pass here that again is not an empty string or a null is going to be considered a truthy value. So isNull and not null, or isNA and not NA, they both work also with entire series or entire data frames, right? So it's not just for a one-off value. You can pass an entire series, and the result back is going to be if the series what values in the series are either null or not null, depending what's the question you're asking, either is null or not null. So in this case, we say which values of these series are null. This is not null, this is not null, this is null, so this is only true. And the opposite for the following method we are applying, or actually function. And again, the same thing works with entire data frame. So something we do usually is if you look into not null and null, a few hacks that we usually apply are the count, and actually this would be the sum of all the null values or not null values. So we have this entire series, and we can say how many not null values we have. And if we sum those not null values in this case, we're going to get a result out, which is the entire summary of the not null values we have asked. And the same thing is going to happen if we say is null. So if I do here is null sum, we're going to get how many null values we have. And it's pretty much the opposite of this question, is null. There you go. And the way it works is in Python, Booleans are pretty much integers. They're ones and zeros. So every true value is going to count as 1, and every false is going to count as a 0. So if you ask for the sum of a Boolean series, you're going to get out the result of the number of truths that are available in that series, right? So in this case, we have 2 null values. We ask how many null values we have, is null.sum, we get 2 out. You can use these tricks to filter the data with a series. So in this case, we can say, give me all the values that are not null, right? It's just not null. Also, something interesting is that both for data frames and for series, the not null, is an A, not an A methods also, functions also work as methods. So in this case, we can say, instead of pd.notNull, we can say s.isNull or s.isNull. So now it gets a little bit more, a little bit simpler. But if the final objective of this call, s selecting only the values that are non-null, was to drop the null values, then there is a simpler form, which is drop an A. Okay, so in this case, we can say s.drop an A, and we're basically invoking the same thing that is happening here. We're just excluding, all the missing values in the series or the data frame, because this also works for data frames. So what's the one important thing to remember here is that all these methods are immutable. We are not actually changing or modifying the original series. The underlying series is not being modified. There is a new series that is returned. So if I invoke s again, this thing is not modifying the series. You're creating a new series, and that's the one that doesn't have the missing values.
To understand why U1 is not is null. I don't think he talked about it though.
Everything we've said also works for data frames. So right here, with this data frame, we can say how many, right? The first thing usually is to start with an info method, right? So we have info, and we see that there are in total 4 entries, 4 rows. We can also do a shape if we need more information about the structure of our data frame. So there are 4 rows, 4 entries in our index. Column A has only 2 non-null values. So that means that there are 2 values that are actually null. There is column B that has 3 non-null values, so that means that 1 value must be none, and that's for column B again. So usually info gets you very close to understand the structure of your data frame and how many values there are missing. The same thing happens with sum. We can just do df.isNull is an A and then sum, and we're going to get a quick reference of how many null values we have in that given data frame. Drop an A works in the same way, but there is a significant difference. The way drop an A works in a data frame by default is by dropping any row that has at least 1 null value. So this row has a null value dropped. This row has a null value dropped. This row has 2 null values dropped. This is the only one that it's not being dropped. Right? So it's very harsh in that respect. You can change that to make it to the column. Only keep the column that has no null values, and that's by switching the axis equals to 1. And there is also a way to select a subset or threshold. So only delete rows that have less than 3 valid values, for example. In that case, you're going to use something like the strategy of the drop an A. You're going to say drop the columns, the rows, or the columns, because this also works for columns, that have all the values in null, or drop this is the default behavior, drop all the rows that have any value in an NA, or specify a threshold, which you are basically saying, I need this amount of valid values in order to keep the row. It's the way it works, not which ones to drop, is which ones to keep based on the threshold. So once you have identified the null values, it's extremely simple to clean them, to fix them. So the first method we're going to see is fill an A with a particular value. We're going to say from this series, I want you to fill the blanks or fill the missing values with, or fill the NAs, fill them with number 0 in this case. So these 2 are number 0. Or of course you can use any statistical method you want. In this case we can use the min. Remember, this is not altering the series. The original series is still the same. We're not changing it. It's creating new series because all these methods are immutable. The following method is, or the following way this method works is by passing a method, which is for field or backward fields. These are the possibilities. And basically the way it works is it's overflowing all the values top down, at least in for field, right? Starting here, it's dropping this value here, dropping this value here, and dropping now 3 here. As this thing is a none, it gets replaced. So this thing is 3 now, which gets dropped here, and now this thing is 3 again. So that's what we have right there. And of course, backward field works in the other way. Starts with 4 and moves it here, and then moves it here, etc. You have to be careful when using this, because if you have null values at the beginning or the end, then you're going to end up again with null values, because there is nothing to feed forward, right? This is the first value you have in there. And all we've seen also works for data frames. So both backward field, forward field, or both in terms of rows for filling, right? So we have these data sets. So we do forward field row base, going to be 1, 2, 2, here 2, and then 5, right? So that's going to be forward field axis 1. If you use forward field axis 0, then it's a vertical filling, right? It's going to go here 1, 1, 30, 30. So that's for the column that's right here 1, 1, 30, 30. So it's either forward filling this direction for filling, or it's going to be in this direction, depending on the axis that you are passing. And actually, let me put the correct forms. With axis equals 0, it's going to be columns, it's going to be this direction. With axis equals 1, it's going to be row-based, so it's this direction, right? So we had a null value here that's going to fill in this way. Okay, moving forward, what else we have? We have here checking for values, and we're pretty much saying this already. You can use the isNull, the sum method to get how many values you have, and there's also any and all, which will give you very quick. These are usually called Boolean tests. You can say ask if there are any values are valid, or if all the values are valid. It's just to build more complicated queries. So far, so good. So the process we said was at the beginning we were fixing missing data, missing values. There is nothing in there. We have read a data frame. Where's our data frame? Right here. We have read our data frame from CSV, from a database, and the value is missing. No, there's a hole in it. So we have quickly identified it with is an A or is null. We were able to drop the ones we didn't want to keep, drop an A, or we were able to fill the values we wanted to fill an A. That was simple. Is an A, drop an A, fill an A. What happens when you're cleaning data that actually has a value, so there is nothing missing, but those values are invalid. So for example, here, the sex column is a categorical column that only accepts M and F. D and question mark, those are invalid. It's very simple to see an invalid value here because it's completely out of the scope. The same thing as we have, for example, question mark in the age column, or if we have a string in the age column. It's very simple to identify that. How are we going to clean those? Let's start with sex first because it's simpler in this case. The first check we can do is with either unique or with value counts. I'm going to use value counts. We've seen this method before. It's a quick summary of all the unique values you have, and in this case, value counts also gives you a total count for those values. How can you fix them? Well, there's a replace method, which is extremely intuitive. You can just replace. In this case, we're changing all the D's to F's and all the N to M's, and it can work in multiple columns. For those values that, again, we said were more complicated to fix, like in this case, we know age, in this case, is 290, and we know, because we know the domain, that 290 is an invalid age for a human. So we will need, usually in those cases, we're going to need more complicated fixing, and it will involve more programming. That's the reality. You have to be better at coding. In this case, we know that this value is invalid because it's probably an extra 0. So all these values, you are pulling a CSV with ages, and there are a ton of 180, 290, 32, 320, for example. Invalid values out of 100, right, in the 100 places. And that's because there were typos when they were creating the ages. So how are you going to fix that? Well, in this case, it involves a little bit more programming. We're dividing everything by 10. So also something that might be useful is dealing with duplicates, and we need to first define what's going to be a duplicate value. So this is usually a little bit more political if you want. You have to define what's going to be a duplicate. In this case, we have a series and it contains ambassadors, and the ambassador is the index. The country of the ambassador is going to be the value, right? So this is usually the important part. The rating here says that we're conducting a party and we want to invite one ambassador per country. We don't want to repeat ambassadors. So in this case, what's going to happen is that these two, in our humanized at least, we can clearly and quickly see that these two belong to the same country and these three belong to the same country. But here again, we have to define which ones are the duplicates, if you want, and which ones are not duplicates. So for example, maybe we can say the first one is duplicate, or we can say the last one is duplicate. So this is the first one, not duplicate, or actually we can say the last one is the one I want to invite, it's not the duplicate. So we're going to have political rules, if you want, for each one of those. So let's see the duplicated method and the way it works by default. By default, the duplicated method is going to return true for duplicate for all the I'm going to invert it. It's going to not treat as a duplicate as the first instance that it says. So the method is actually walking top down, right? And it's saying, do I have friends? No, I don't have friends. I'm going to keep it here because it's the first time I see friends. Do I have the UK? No, I don't have the UK, so it's going to keep it here. Then it sees the UK again, realizes the UK is already there. It's already present. So this one is going to be considered a duplicate. Italy is here. It's fine. The first occurrence of Germany, it's fine. Writes down Germany. But then it says Germany 2 more times, and it realizes that Germany was there. So those are now duplicates. That's the way it works by default. We can change that and change it to last. So the last element is not considered to be duplicate, and the other two are considered to be duplicate. And the same thing here. Kim here is the one considered duplicate. So it's either top down or bottom up, depending the way the parameter you're passing. It's either keep default or keep last. Or you can be a little bit more harsh and say everything duplicated is actually needs to be considered duplicate. So these two are duplicates and these three are all duplicates, as you can see right there. Similar to the duplicated method, which pretty much tells you which values are duplicated, it helps you identify them. You also have the drop duplicates. And in this case, what this method is going to do is basically the same thing as before, but dropping all the values that check for true, right? So if the method if the value is missing, it's going to just drop it. And the same rules apply: default, last, and false. For subsets, in this case, what we have is we have multiple players in the data frame, but what happens is that this player, Kobe, is present 3 times. For humanized, we see Kobe 3 times. What's going to happen here is that the way we're going to think about duplicates is by understanding the correct subset that we should check. In this case, Kobe playing as an SG is duplicated 2 times, but Kobe playing as an SF could be considered a different player if you want, because maybe it's a different season or it's a different position they played. So in that case, we need to pass what's the subset that we are going to consider duplicate. Only check for the column name, or check for the column name and or not check for the column name, which is the default. It's going to check the entire data frame, and when that happens, then these two are considered to be duplicates. So this one is a duplicate with this rule. If we put keep false, both are going to be considered duplicate. So this second occurrence is the duplicate one, and the last one is a completely different row because the value in position is different. So that's the way it works here. Moving forward with more cleaning of values, we're going to talk about string handling. And this is a very neat feature of Pandas that special types of columns will have special attributes. So given the column type, so df.info, which is an object, which is a string, right, in Pandas, all the strings columns are going to have this special attribute, which is str. All the datetime columns, something we're not going to cover, but you need to know, all the datetime columns have a .dt attributes. All the categorical columns have a .cat attribute. And those attributes, str, dt, cat, they have special methods associated with the domain of that column. All the methods associated with string are, of course, for string handling, or the methods associated with dt are for datetime handling. So in this case, we're going to review a very good subset of the string methods we can apply. And something interesting is that all these methods have a lot of relevance, and are related to the ones in pure Python. So if you have a pure Python string, there's a split method, there is a contains method, or I don't know if there's a contain actually, I think it's the in operator, but there is a strip, and there's a replace, right? So most of the methods under the str attribute in Pandas have an analogy in the standard library of string handling with Python. So starting at the beginning, this is the data we have. I'm going to delete this. This is the data we have. What we are going to do is split the values, right, by an underscore. So in this case, that's what we have. We have split all the values with that underscore. And we're going to use the special attribute expand equals true. And what it's going to do, it's going to create a data frame out of that. So we create a data frame with 70 columns, and this is what we have now. So we can keep applying methods. So for example, contains or contains regular or contains with regular expressions, right, for you to see the power of it. We can do strip replace, and we can do even regular expressions with replacing. So we could fix something like this question mark in a string. We could fix it with regular expressions if you know how to handle it. And finally, something that is going to be very helpful when you're doing data cleaning is looking at the data from a visualization perspective. Data cleaning has a ton to do with statistical understanding of your data too. When a value is considered an outlier, for example, it might be invalid and you want to clean it. But that's a lot more about statistics. In this case, I want to show you very quickly the matplotlib library that I've been promising for some time now. The matplotlib library that so far we've accessed it directly from Pandas, right? We were doing a data frame.plot. This library, matplotlib, is the one backing all those methods, and we're going to see how to use it directly now. The matplotlib library has two important APIs, we're going to call them. One is the one that I don't prefer, which is the global API, but it's the most common one. It's the one you're going to find around the global API. And the second one is the object-oriented API, so it's around here. And usually there are ways, it's just two different ways of doing the same thing, okay? The global API is an API that's inspired in MATLAB. It's been around for a long time, and sadly, most of the answers you find in Stack Overflow, tutorials, books will be using this global API. The one I prefer the most, and I'm going to explain you why in a second, is going to be the object-oriented API. But I want to show you both so you have a reference. If you follow me in this feeling of preferring the object-oriented API, you will always have to translate global to OOP. Why is it considered a global API? Well, we have imported matplotlib.pyplot as PLT, so we have imported the whole module, the whole Python module, depending how much you know about Python programming, this is going to make sense or not. We have imported the whole module. Now, what we're doing is we're invoking plt.figure, and then we're going to do a title, and then finally we're plotting two things. We're plotting x, and we're plotting x squared and minus x squared. And why is this global? Because we're invoking functions that are at module level, and there is an object, the final plot, that is being modified by these very generalistic and global calls, right? So by doing this call right here, I'm modifying the final result of the plot. Let me show you a more complicated example so you see the problems with the global API. If you look at this line, if you could delete everything, let's actually delete everything. What is this line doing? Which plot is affecting? You do not know. There is no object-oriented way of saying, in this second plot, the plot on the right, or the figure on the right, or actually the subplot on the right, I want you to plot this thing. You're just saying it to the entire module. And depending the order that you set it, is where it's going to land, that particular figure, where it's going to land, in which plot it's going to land. Again, it's a global API, so we start saying, I'm going to create a figure, trust me. So from now on, I'm going to start drawing on it. This is going to be the title. And hey, by the way, it's going to have one row, it's going to have two columns, and I'm going to start drawing in the first plot. This one right here on the left. Okay, so now I have kind of activated, if you want, that plot. It's active. So now I'm going to start drawing on it. So every action that happens after this line is going to be affecting this plot, right? So then I plot x and x squared. I plot this vertical line. I put a legend. I set labels, etc. And at some point, I just stop and say, hey, now I want to switch the plot. I want to now start plotting. I want to start plotting here in this second one because I have just changed that. The first line, this one. Oh, sorry. The way it works is by saying the first row, second column, but second plot. So now I want to start plotting in here. Every successive line will affect that plot. And again, you can see that understanding a code, given the order, the order in the sequence of lines, is very hard. If you have to debug a report that has a plot that takes 100 lines, then you have to keep in your brain what's happening top down. A different approach is going to be the object-oriented approach, in which we're creating a figure and we're creating axes. So in this case, we have right here one entire figure in red, and we have in here purple we have two axes. So this is axis 1 and this is axis 2. So we have two axes. We're going to create those using an object-oriented approach, and we're going to keep references to them. So we're going to say later to these axes, I want to plot something. And that will be very explicit. It's going to be an object-oriented way. So the first thing is creating the figure and the axis. In this case, we have just one axis. That's it. But you can have more. And then you say, in this axis, I want to plot this thing. In this axis, I want to plot that thing, etc. When you have multiple axes, as I could show you, I'm going to go back again to that in a second. But in this case, in which we have 4 axes, right? So we create one figure, and it has 4 axes. So we do it with this subplot method, saying n rows and columns. Now we say to the axis number 1, I want to put this thing. To axis number 2, I want to put that thing, right? So it's 1, 2, 3, 4. And now it's a lot more explicit. It's not depending on the order. I could change this order. That doesn't matter. Oh, there. That the results are going to be the same. Axis number 4 has yellow regardless of the position that we're following. So the matplotlib, and now that we have clear out the differences in both APIs, matplotlib has this very simple plot function or method, depending object-oriented or global, that will plot something that you specify. In this case, we're passing all the values in X and all the values in Y, and in this case, we're passing a given line style. This can change with this type of syntax. You're saying, I'm plotting this thing in X, I'm plotting this thing in Y, second parameter in Y, and I want you to use a straight line, yes, with this marker, the dot, and in green. So this is if you are very familiar with it. If you're very familiar with matplotlib, you can use the syntax. In other case, you can just say line style, marker, color, specific keyword arguments for each one of those. So do we only have line plots in matplotlib? No, of course not. We have a huge variety of plots. And by the way, there is another one here if you want to see more advanced grids. You can create these grids and put different things in it. And again, not only line plots. One good example is a nice scatter plot. So basically, we're plotting X and Y, correlation, and there is also a value, a color map, right? So given the value, there is going to be a change in color. So this kind of lets you plot 3 to 4 dimensions of your data. The value in X, the value in Y, the size of the bubble, and the color of the bubble. So you're pretty much encoding 4 dimensions in just one figure, right? So in this case, we're just using 2 different scatter plots. There's more information here. We can also plot histograms. We've very quickly seen that with Pandas. With Pandas is very simple, which is plot type histogram, hist actually. You can look it up in our previous lessons. So just go back again to the index in the video. And the histogram is extremely simple. Just text the values you are plotting and how many bins you want. There are some more advanced arguments here, like the alpha level, etc. But it's simple. And similar to the histogram, you can also create kernel density estimator diagrams, which is very similar to a distance to simulate if you want a continuous distribution. You can combine these plots if you want. In this case, we are creating the plots. We're plotting a histogram, and then we're plotting the lines, and then we're changing the limits, but that's pretty much it. And you can also create bar plots, right? So in this case, we have tlt.bar, or here we have 2 bars are stacked, right? That's the different way to look at it. And finally, checking outliers, you can always plot histograms or box plots, right? So box plots are also a nice feature to have in here. So this was all with data cleaning. We're going to keep moving forward this tutorial. I want to mention one more thing here. And there are notes here for kind of a task that you can follow with data cleaning, which where we are identifying missing values in given positions with is null, is an A, and right here we're looking into more detail about some statistical properties of the data in case we need to clean it. Okay, so this is a little bit more advanced, and it's related to the concept of cleaning data given the domain. So the statistical analysis can tell you that this value is an outlier for this distribution. The value might be valid. So for example, a human being is 90 years old. That's valid. That's a valid age. But if you're analyzing data about high school students and a human that it's 90 years old, it's going to be completely invalid, or it's going to be an outlier in that distribution, and you can treat it as an invalid value and clean it out, remove it, for example. So that's still a little bit more with the whole statistical analysis that you can follow here. It's a little bit more advanced for this tutorial. So let's move forward with the rest of the videos. And now it's time to get into more advanced features of Pandas to import external data. So we've seen already in a real-life example the way we can import data from CSV files and from Sql databases, right? We had actually those 2 lessons. The objective of this part of the tutorial is to show you how you can improve or get into more advanced use cases of...
Let me see if I can finish, if I can get the right answer before the video. So I was opening the file here, SFB. I think R stands for reading. Then it's looping through the file. It's equating the values for each loop. Iteration should be this. So I have to fill this, I think, A, B, and C. So A is going to be certificates SCV. Delimiter, I'm not sure. I think is this $sign. It's where it's going to stop each thing. And then search num. So that should be this one.
of importing data. So we're going to start, for example, with CSVs and text files. And again, you've seen it already, but here we're going to give it an extra twist. So I'm going to show you more advanced features and for special use cases. TXT files, CSV files is, conceptually speaking, a CSV file is a text file. It's just humanly readable text, right, that it's encoding information. The idea of a CSV file is that it's tabular, right? So it's a plain text file that contains tabular data in it, and it's separated. CSV stands for comma separated, but it can be separated, it can be anything. We can see more examples later. But basically, the idea is that it's text file, that it's tabular in a tabular format. So that both CSV files and text files will be read with the same method. So to get things started, I want to show you the basic way we read data from external sources using Python without even starting yet with Pandas. So you don't need to know this. It's usually productive, if you want, for data scientists or data analysts to understand a little bit more how file reading and writing works in computers, because there are multiple concepts aligned here. They involve operating systems, processes, your language, right? It's not the same thing to read a file with R or with Python or with another language. So there are multiple concepts here. And even though Pandas in this case is going to make it very simple to read and write data, you can get a little bit of a more advanced use case if you know the internals of, again, both the operating system, processes, and your language. So this is the way we read data read a file, using pure Python. We use the function open. And in this case, we're using a context manager, just a security feature, again, related to the advanced usage of reading and writing files. But it creates a file pointer, right? And with the file pointer, you can then use the very simple API post, but that pointer, which is something like readlines, read a number of bytes or characters, or you can just even treat FP as an iterator, just do for line in FP. But basically, we're going to do something like this. We start reading data from top to bottom, just until, I don't know, we hit a given end. In this case, we're doing it just for, I don't know, a couple of lines. What else? It gets very difficult when you're reading text files to process them, because it's usually hard to parse the structure of the file. So it's not the same thing to have a file that's separated by commas, separated by colons, separated by pipes, spaces, etc. So you're going to see that once you want to get a little bit more, with an advanced usage, right, or a little bit more fancy in your calculations and the way you parse the data, it's going to get harder. So that's why we're going to use Pandas, or I'm going to show you in a second, the CSV module that is part of Python. So this is the file that we're going to be reading. It's the exam review file, and I'm going to open it. And even though it doesn't look like a CSV, it is indeed a CSV. The difference is that here the separator is the greater sign. It's not the comma, it's a greater sign. That's going to be what marks the delimitation between different fields in our CSV file. So we're going to use the CSV module, and the way right here to parse the data using that module is by passing a special delimiter, right? So that's going to be the type of work that you might need to do when you're parsing the data. It's not the same thing to have a delimiter that it's a greater sign. It's not the same thing to have numbers, for example, that are enclosed in quotes. All those things, right, will change the way you work. And all this is going to be abstracted away by the Pandas module. So to get things started, again, with Pandas at least, Pandas has multiple read underscore something methods that will work for different sources, right? So we saw already read SQL, we've seen read CSV. There's also a read HTML to directly parse information from a table. It's literally, you pass a website, it's going to read information from a table, or read JSON, read more advanced formats like Parquet or Stata, etc. And again, each file format will usually have a correspondence in Pandas. I've never had the chance to rewrite my own stuff, to be honest. The same thing is going to happen for something like Excel, which might need external modules. It's not directly provided by Pandas, but by installing those modules, you can easily incorporate Excel files in your day-to-day work. So the read CSV method, has a ton of parameters. So this is the main characteristic of all these read something methods. Given the amount of possibilities that you're going to have with these files, there exists a ton of different ways to customize the method invocation. Right? So again, CSV files, we saw there are multiple things happen. CSVs that have a header, don't have a header, different delimiters, different enclosing of strings or numbers, multiple things, blank lines, etc. Multiple things are going to happen, and that's all you're able to customize all that with the read CSV method. So this is the reference of all the attributes you can pass to it. Usually something that I do, and I do this very often, and I use Pandas a lot, and I still do something like read CSV, and I get the documentation right here to look into the parameters that I think I need to pass to my particular use case. So keep an eye always in the docs, because it's impossible to remember all the parameters in the CSV. So in this case, what we're going to do, it's something very interesting, is we're going to parse a CSV file, but it's not located in this computer. It's not locally available in the computer. The CSV file is this one right here, which actually is the source. If I get the raw version, is this thing. So this is a CSV file. What I could do here is download the file, right? So just do file, save, get the CSV file on my computer, upload it here, right? So just copy and paste it here, drag and drop it here. But actually, Pandas has this nice characteristic that it will read a CSV that it's either locally, as we did with BTC Market Price, or it can also do it remotely. It's automatically going to download the content of those files, and it's going to provide, it's going to save it in memory for further usage. So this is a very neat feature. And again, this is the CSV file that we are using. And again, the same thing, if it's a local file, it works in the same way. So a few features you've seen already. In this case, we can do header none. If you don't want to treat the first row as a header. Or what about missing values? We can treat some of these values, like a question mark or like an exclamation mark or a dash, etc., as not a number value, right? So as a missing value. And now any of these values we have passed will be transformed into another number for an easier process cleaning. We can pass names, which is going to be basically the column names for each one, and we can also specify column types, as you can see right there. So now the types are going to be float and object. We've done this already in one of our lessons. We are parsing the time, and there you go. So putting all together, we get to these advanced forms of reading CSVs, where we're passing column names, we're passing types, we're asking to read dates, we're passing no values, headers, etc. So this is a pretty common thing we are doing. So what about exam review? If we try parsing this thing, we get this very ugly format. In this case, the parameter to specify what we used to call delimiter in CSV is now set from separator. So the separator is going to be the greater sign, and that just works as it needs. So a few more examples you can check on here. The most important part is following, right, the documentation to find those particular use cases that you are having. So for example, something like skip blank lines, or whenever there are like empty rows at the beginning, right? So if you have empty rows at the beginning, it's something you can also say skip rows. So you don't need to parse those. It's not going to break, etc. So that is all part of the CSV file. And to finalize this part, at least CSVs.
I'm interested to see whether how the challenges are going to be. I imagine they're going to be a lot harder than the lessons, and that's where I'm really going to learn how to use each thing. I think I learned a lot more on the previous section by doing the challenges than watching the classes, and the challenges were a lot harder than the classes, than what was taught in the classes.
And now it's time to read data from databases. We have already done that in our real example with Pandas part of the tutorial, but I want to show you a little bit more details so you understand how data is being processed in case this is a common scenario from you, importing data from databases. So the libraries you will need, first thing, depending on what database engine you're using, Postgres, MySQL, Oracle, etc., you will need to install different libraries. But the APIs, once you have installed those libraries, are going to be the same. There's actually PEP from Python that actually defines the interface for database libraries, and Pandas can work with pretty much any database of these SQL common database that comply with that interface. In this example, we're going to use SQLite because the database is right here. There's nothing, no server to connect, etc. It's extremely simple to get started. And the example we're going to use, or the database example we're going to use, is actually a different one from our previous database rating. In the previous one, we were using Sql. In this case, we're going to be using Chinook, which is smaller, both in structure and in size, so it's going to be a little bit simpler. So to get things going here, the same thing we did with our previous part, that was how to read data from files. I show you how to actually read data using Python. So forget about Pandas for a second. I told you if we go back again to the beginning of time, there was no Pandas. This was the way we were reading files: open, FP, read lines, etc. So I now want to show you what predates to Pandas, what was the default way to read data before Pandas, which is with the regular again interface from Python. So the way it works is we're going to import SQLite library. We're going to create a connection, and now with this connection we have this common interface that again is common for pretty much any other database that you're used to. And the default behavior is we're going to create a cursor, and we're going to execute queries using that cursor. In this case, we're going to execute a regular select star from employees limit function. We want to have five records out of the table employees. Once you have executed the query, it's like there waiting. You can do a fetch all to get all the results of that query. And here are all these results. As you are noticing, this is the result is a list of tuples, so it's not extremely useful. Now, if you combine it with Pandas, you can just create a data frame out of that info and work close. It's not perfect, but work close. So let me show you now, before we're going to close the cursor and the connection, let me show you now how we work with Pandas. With Pandas, we have a read CSV method. We also have a read SQL method. And in this case, what these methods are going to receive is the first parameter is going to be the query that we're passing, and the second parameter is going to be the connection that the connection object to actually issue the connection by Pandas. So it gets as simple as writing the query, and now everything has been imported into a data frame, including column names and all that. If you want to get a little bit fancier, you can either specify the index column that's going to be used, of course, as the index, and also what types to parse for a specific column. So now we have pretty much all the work done. So we're going from something very manual, as processing things with a cursor, etc., which might also be slow, to using Pandas to directly import the data from the database. There is actually a caveat here, and I'm going to tell you, it's kind of a very deep detail of the way Pandas works, and is that the read SQL method is actually a shell for two other methods: read SQL query and read SQL table. All right, so read SQL table and read SQL query. When you're using read SQL, it's actually kind of forwarding the work to either a query or a table. Read SQL query is the default behavior, what we've done so far. So in this case, it's just going to issue a query and the connection is going to read it for you. In contrast, read SQL table is going to read an entire table. You just pass a name, and it's going to automatically give you all the information for it. So in this case, all the column names, etc. So it's a lot simpler to read an entire table. The only thing to keep in mind is that to use this method, you need to install these libraries, SQL Alchemy, and the connection is generated from it. So in this case, we create an engine and we create a connection object, and now we can pass a connection object for Pandas to do it. So again, it's pretty much the same. If you find yourself doing read star from this table, read star from that table, it's a lot easier just to read SQL table, and that's gonna do it just at once. As we saw that read CSV files had read CSV method had a two-CSV method. The same thing happens with read SQL. There's a read SQL and there's also a two-SQL. What it's gonna let you do is get from the database and write it down into a database table directly. So it's gonna also receive the connection, right? So two SQL is gonna receive what table name of this data frame, what table name is gonna be, and a connection object. Now, something to keep in mind is that two-SQL has an important parameter, which is what happens if the table already exists. In the default way, it's going to fail. It's going to throw an error when you are trying to save data to a table. And this makes sense because as data analysts, we're usually reading data and processing it. We're not so much writing it, so we want to make sure that it's not by mistake. But if you do actually want to write data, you can just change this parameter if exists to something like replace or append. Usually we're writing to intermediary tables. Again, you can choose either to replace the whole content of the table, be careful here, or to append, right? Just write it at the end of the current table. So that's just for SQL. So this was the way to read data from databases. Of course, we're not touching on anything like SQL and all that. It's a lot more advanced. It's just for you if you already know SQL, if you're already working with databases, you can pretty much copy and paste what we're doing here, and you're going to get your data imported into Python. So let's move forward to read some HTML files. And now, very quickly, I'm going to show you how to read tables or data frames directly from HTML web pages. To be honest, this is a simple method. It's going to be just read HTML, but it depends a lot on the structure of the web page. So if it's not well structured or the tables are not correctly created, you're going to have issues and you have to do a ton of data cleaning. In my experience, whenever I'm trying to parse a table from a well-structured site like Wikipedia or some stats site, it usually works very well, and it's a very quick way of hacking. Whenever you have questions, like, I don't know, I need to know the GDP of countries. Instead of looking for a GDP data set, you can just go to a Wikipedia page. There's usually a table there. You can directly parse it, and you are done. So again, it's a relatively simple way to get some data for quick hacking and exploration. The way it's going to work is we have these HTML created. It's just for testing purposes to get started. Usually, of course, you will try to read something from a live website, so you're going to pass the URL to the read HTML method, and the read HTML method will download the content of the page and parse it. Let's suppose we have the content already, the HTML, and this is what it looks like. There's exactly the same HTML we have on top. I'm just displaying it here in the notebook. And what we're going to do is we're going to invoke the method read HTML. The read HTML method is going to parse the entire HTML and look for multiple tables, not just one. Sites will potentially have multiple tables. Even if you don't see them, it's a common way to structure things in HTML to use tables. That's why it's going to parse multiple tables. In this case, we sort them all in the DFS, multiple plural, right? Multiple data frames, and we see there is only one. So in that case, we're just going to get the first data frame, and it has correctly parsed what we had before, just working in the same way. The same is going to happen with, for example, things for headers and all that. If the table doesn't have a header, it's going to automatically, right, understand that in that case. So that's pretty much as we know it already. In this case, what you're going to see is that what I told you before about data cleaning process, that this table does not have a header like the previous one that has a t-head attribute. In this case, a header is just another row. So that's why read HTML is going to have issues, and you have to provide a little bit extra information. So let's see another more realistic example, and we're going to parse data directly from a website. Let me tell you here, this is just for educational purposes. You always need to understand if the data is public, so you can actually parse it. Again, for Wikipedia, at least what I do, the content is Creative Commons, so you can get a hand on it. What we want to show you here is that a very complicated table that has multiple headers, etc. So that's why we're using this example. So we're gonna get the URL, and we're gonna directly do NBA tables equals read HTML. The only table in this page is this one, the large one. So that works. And now we're going to get NBA. It's going to be that. And we see that all the players in this case have been parsed. What about something else? Let's actually open this page right here, Wikipedia for The Simpsons. And here we will probably find several tables. See, we have one right here, this one. There you go. So I'm going to import it. We have 27 tables. Again, you don't see them, sorry, but they're there. And the most important one is the one we care, is this one right here. So the problem you're going to have with this table is that it's using both column spans and row spans. So in this case, this column here spans for 1, 2, 3 columns, and this row here spans for 1, 2, 3, at least 3 rows. So that column spans results in this very ugly data frame, and you will need a little bit of extra cleaning. So the problem you're going to find with HTML tables is that usually there are things that are not well formatted for machines. They're formatted for humans. So for example, in this case, we have this header repeated. When you parse this data, you're going to find that every 20 rows, there's going to be a header row, and you will have to clean it. For, in this case, 20 rows, you will need to drop. You will do something like df.drop. Let's see actually if we can say it. I haven't tried this, but let's just do it live. .head, and you're going to find 25 records now. So here, record 22, we find that header. So what we're going to do is you will need to do something like df.drop, range 22, starting 22 up to df.shape at 0, right? These many rows, plus 1, and every 20 rows. I don't know if this is going to work. Let's just run it. Oh, it didn't even work. It didn't compile. There you go. This is NBA actually. There you go. So maybe it worked, you can check it, but what I'm going to say is, again, there is some cleaning to do because HTML pages are optimized for humans, not for machines. So usually it's going to take a little bit more time. The good news is that there is usually a service associated that you can consult. So for example, there is a Wikipedia API that you can use instead of a page. But again, sometimes it's just easier to pull the data directly from Wikipedia. So that's it. You can also write data to CSVs, of course, or HTMLs. That's pretty much the standard, as we've said. This is all we had for the read data portion. And we're going to move forward now with a few other methods, especially what we call data wrangling. We're going to do a little bit of grouping and keep moving forward with our tutorial. We have decided kind of last minute to add a final source of external data. That's going to be an Excel file. It's just a common Excel file, as you know it, because we imagine that you might come from an Excel background, so you can just export the data you have in your Excel files, spreadsheets, and load them into Jupyter Notebook and start working with them with Pandas, so you can try things out and kind of draw the parallelism between Excel and what you do with Pandas and Python. So the first thing is that an Excel file is not a text file. So if you try getting the content of it, it's not a text file. It's not so simple to parse it. So that's why it's going to require external tools that they are already installed in Notebooks AI. They might be installed in Golab, but it depends on your computer how you're going to install it. So just keep in mind that there might be issues when importing data from Excel if there is low compatibility between the library you're using and the spreadsheet version you're using. But without getting into those details, there is this read Excel method which pretty much takes care of everything for you, has different parameters like finding the sheet that you're reading from, of course, the path, etc. So we're going to start reading this file, which is products file that has 3 sheets: products, descriptions, and merchants. And it's actually something we use in an Excel file in our data analysis from Excel to Pandas scores to show how to merge data and all that. And from this file, what we're going to do is just read Excel. And what you're going to see is that it reads the first sheet of the Excel file. I mean, a data frame just corresponds to one sheet only, right? And the first one is products. So that's what we are reading. There are different behaviors for it. So you can change the way you parse headers, etc. You know it already, defining a specific index. That's pretty much everything we have seen so far. Selecting specific sheets is simple. Just pass the sheet name, and you can read either products, merchants, whatever sheet is available in the current Excel file. There is another format or a specific class that is a little bit more advanced, that it's the Excel file class. So it's not, as we were doing here, read Excel directly is going to read that Excel file into a data frame, but you're going to instantiate this Excel file class with the parameter being the file name. And now these files can have just a reference of everything you have. In this case, we can do, for example, sheet names. It's going to tell you have products, descriptions, and merchants. This is a little bit more explanatory data analysis. So let's say you can't use Excel to actually see the contents of the Excel file. This is going to be helpful. You're going to first parse the Excel file, get the sheet names, and a little bit more of an understanding of it. And now we can say from this file we have previously parsed, it's right here, or instantiated, we can parse the product sheet, and that's going to get you that data frame. And the same thing is going to happen with all the parameters we can pass. They are the same as read Excel. Finally, you can see that there is also 2 Excel file, and it works pretty much in the same way as 2 CSV. You can decide if you pass an index or not, and also you can find if you're going to pass a sheet name or not, or it's just going to be the default one. So as you can see, getting your data into from an Excel file into a CSV data frame, is extremely simple. There are more customizations to do. Let's say all your file is shifted, right? Either rows or columns. You can change that with star row or star column. That's going to work too. So that's pretty much the only thing we need. If your writing process is a little bit more complicated, like for example, you want to write specific sheets in a multi-sheet Excel file, you can use what we call an Excel writer, and it's also part of Pandas. So you instantiate the writer, and then you can start the write process, saying which sheets you want to write with each one of those data frames. So again, reading and writing data from and to Excel files is relatively simple. It all depends on the libraries that are installed. It depends on what libraries you have in your current environment, if it's Windows or if it's a Linux / Mac. The documentation of pd.read Excel might have more details for the given platform that you have. So let's see if it names per document. If it's not here, it's going to be in the Pandas documentation, but there might be requirements for each one of the platforms that Pandas is supported. So just check it out. Check for your own platform, if you're in Windows, Mac, Linux, how to get those libraries installed. So in case you're just getting started with Python and you might come from another language, the objective of this quick section is to show you Python, ideally in under 10 minutes. I think it's going to take a little bit more, but this is a very, very, very quick reference of Python. Again, just the high-level features of the language, how to use it, how to code functions, how to import modules, variables, data types, collections, etc. You can just scroll through this notebook if you want to take less time. I will be providing explanations on top of all the topics, but this is a very good reference of the entire language. So to get things started, Python is an old language, period. It has caught more attention in the past 5 to 10 years, but it's a very old language. It's even older than Java. It's up here in 1990s, and it was created
Go skip parts of this.
By this person, Guido van Rossum, features of the language, etc. Supports imperative programming, and it has a wide variety of applications you can do with language. And I hope was deprecated in 2020, so you should not use it anymore. There are still ways to install Python 2, but it was deprecated, so you are not very hard. So to get things started here, I will be drawing the parallelism with regular syntax. Usually this is just 4 spaces.
Yeah, I already watched all this stuff.
The correlative types, and these might cause confusions, but basically you can assign variables to any. To be honest, on Python 3, to be honest, we use just integers. That's the way we work. There was a difference in Python 2 between Unicode and strings, etc. In Python 3, that has all been fixed. So in Python 3, this is all Unicode, and there is the concept or the difference in terms of the concept of something being the Unicode code points, as it's the string, and the underlying encoding will turn it into binary. So in Python 3, we have a few ways to differentiate between whether it's a binary string or whether it's a text-based string. You shouldn't worry about it. I just want you to know, if you're reading a Python 2 tutorial, for example, you might find the difference between Unicode strings and regular strings, which is no longer something that we should be worrying about. If you have a string that's too long and it expands multiple lines, you can always write it using 3 quotes, can be double quotes or single quotes. So just to create multi-line strings is extremely simple. Booleans, there are two Boolean objects that are unique, right? It's kind of a singleton, which is the true and false objects, for example, and they are of type bool. There's also the concept of null in Python, which is none. We don't have null, we have none, but it serves pretty much the same purpose. In Python, everything is an object, so even these strange objects like none will have an associated class if you want. Everything in Python is an object. So all these what we have just shown. So functions again. Def is the keyword we use. We don't use.
I think I'll skip this one as well.
Function we use def. You can use define as a mnemonic. Right. So by default,
Just gonna be talking about.
Only going to return if this happens. If something can be coded with a for loop, it should be coded very quickly. A list is l.append. In this case, it's going to be decision number 1. Tell you about dictionaries. Both. This is extremely fast. It's what we call O1. And this is because, as you might have seen, so again, as I told you before, we're gonna iterate over collections with the for loop. So in this case is, if we have a list, it's gonna be for element in list. There you go. If you have a user dictionary, in this case, user dot values. There you go. Library of, and you can check the docs right here. Exceptions. This is just an introduction. It might be useful if you are coming from another language, especially to keep this notebook as a reference. We're going to be using Python a lot, of course, and it's a great language.
What? There's more. That would be the challenges already. And there's 9 more.
Today we're going to be going through the Numpy library, which is considered to be kind of the fundamental package for all scientific computing in Python, so it's a super, super important library. To begin, Numpy is a multi-dimensional array library. So what that means is you can use Numpy to store all sorts of data in one-dimensional arrays, two-dimensional arrays, three-dimensional arrays, four-dimensional arrays, etc. And so the common question you kind of ask, or I'm commonly asked when you first bring up Numpy, is why do you use Numpy over lists? So the main difference comes from the speed. So lists, they are very slow. Meanwhile, Numpy is very fast. And so why are lists slow and Numpy fast? Well, one reason is because Numpy uses fixed types. So what that means is, imagine we have this 3x4 matrix, 3 rows, 4 columns, and it's all integer values. And we're going to kind of look at how those integer values differ between Numpy and lists. So let's just zoom in on that 5 that's there in that matrix. So our computers, they don't see 5, they see binary that represents 5. And so this is the number 5 in binary, and it's 8 bits, which makes up a byte. So our computers read information in bytes. So when we use Numpy, this 1 bit 5 is actually by default going to be casted to this int32 type, which consists of 4 bytes. And so it represents 5 in a total memory space of 4 bytes. So int32, and you also can even specify, so by default it's int32, but you could even specify that you didn't need all 4 bytes to represent this value. So you could specify within Numpy that you want maybe an int16, which is 16 bits or 2 bytes, or even if you have really small values, int8, which is just a single byte. On the other hand, with lists, there's a lot more information you need to store as an integer. So in lists use a built-in int type for Python, and so that built-in int type consists of 4 different things. It consists of the object value, which has its own bits associated with it, object type, the reference count, how many times that integer has been specifically pointed at, and the size of that integer value. And so if we break this up into the actual binary that it represents, we can take the object value, and that's represented as a long, which is like 8 bytes. The object type, same deal. Reference count, same deal. And then the size, I believe, is a little bit smaller. I think it's only 4 bytes. But as you can see, that's a single.
I think I will. Let's see what time it is. I think I will stop here and then go take lunch and take a break. And then when I come back, I'm gonna watch this section because I want to do the challenges separated from the sections when streaming, so I can record each thing separately. So I'll probably be back in about 2 hours or however long it takes for me to have lunch. We'll see you.